So here we are, and if we minimize it, so we don't have to do anything, right?
You can stop video and move yourself.
Hey, good morning, Nathan. I unmuted you just now.
Hey, good morning, Professor Moyen. How are you doing?
I'm doing okay. No, it was whatever I watched yesterday, Nathan. It was going very well. So
Okay, awesome. Good to hear. I'm glad.
keep up the good work.
Thank you. All right, so I'm almost set up here and ready to go, and we can go ahead and get started. All right, so everybody, we're going to start off where we left off yesterday. This will be the digital control section of the current mode control of a buck converter. As always, please keep sending the questions. I'll try to answer them as they come. I do have 2 questions that are pending from yesterday that were emailed to me, and I think I'm going to be able to address those right after this first module, okay? So once we go through that, then I'll go ahead and answer those. All right, so without further ado, make sure you send in questions. I'm going to go ahead and start this, and we will stop for questions after this video. Welcome. This is Nathan Weezy, Assistant Professor at Marquette University. This section we're going to talk about the digital control of power electronics and specifically current mode control of a buck converter. And we're going to pick up where we left off last section and convert our continuous time controller to a digital controller. So we have the same structure as we had last section. We have a buck converter here in black in terms of topology, and in blue we kind of have our generalized control structure here. And we're essentially going to design this guy, our digital controller, and test it. So these are our buck parameters from our MATLAB script. These are our controller design parameters, essentially our inputs to the controller design. And then these section of code is essentially our controller design. Essentially getting the gain of the integrator, the pole and zero location scripted out here in MATLAB. And then what I've done continuous here is that I've defined our controller in line 29, our plant, our open loop transfer function, and our closed loop transfer function, all within MATLAB, all in the S domain. These are all transfer functions. What we're going to do is convert these to the digital domain. And how we do that? Well, we're going to do it a couple of different ways. So this will be our line 34 will be our transfer function object within MATLAB in the digital domain in a sampling time of t. Let's just take a quick back up. T should be 100 kilohertz, which you can see here. We're also switching to 100 kilohertz, so we're going to sample and do actuator controller at the switching frequency. We're going to create controllers for all 3 ways of converting. There's actually others, but so we're going to do the backward-Euler approximation in line 35. We're going to do the zero-order Hall approximation and the Tustin or bilinear transform approximation. So we'll have 3 different digital controllers. We're also going to calculate the closed loop response in the digital domain using the S domain equivalent, and then we'll look at poles and zeros of our systems and see how they line up. So here's our controller right here for this one right here. Equation 1 is our controller for, this would be in the digital domain for backwards Euler. And then this is the closed loop response. And what we're going to go ahead and do is look at these on the pole zero map. So this should have, it looks like 3 poles, and actually you can see them pretty easily. If we kind of zoom in over here, you can see we have a pole here, a pole here, and a pole here. Okay, and so the other thing I'd like to point out here is the damping, these damping lines. So usually in the digital domain, you'd like to be on this line right here because it's a damping of 1. So we have 1 pole there. But we also have a pole here, which could be 0.8 or 0.9. And we have this pole here, 0.8, 0.9. Hard to see where it actually is here. In MATLAB, though, you could zoom in and look at this. But the big thing you want to make sure of these 2 poles here is that these don't move a whole lot on you. And how do you do that? Well, you want to check to see how these move against parameter variation like C, L, ESR, etc. Output load. And hopefully they don't move a whole lot on you. It just depends. You should exercise those ranges and make sure they don't move, and how this one moves as well. So for instance, you don't really want this one to move towards this way, or you're going to have a heap of trouble keeping your control loop stable. And that may or may not be a function of the parameters of your system, like capacitance, inductance, ESR, or it could be parameters of your controller. It just depends how those work out. As they're drawn here, they're stable, and these are the pole locations here. So you can go ahead and see those. So these here are pretty close to 1, 0. All right, and then you can also see our 0 locations. We have 1 at 0, 1 at 0.8, and 1 at 0.97 for the closed loop response. So let's go ahead and take a look at this now for our digital controller. I have up our continuous time in blue here, response from the last section. And in red here we have our digital controller, and it is the backwards Euler variant. And what you can see here is that at time about 50 millisecond, we have a load jump from, it looks like 10% up to 100% load. And that would be 300 milliamps up to 3 amps. Yeah, right here. And you can see how they diverge. One thing you can do is see the delay. If you zoom way in here in the IL command, you have at least 1 cycle of delay. Could be a little bit more, up to 2 cycles of delay, just because we're sampling. We're not continuous. We're not a continuous system, so we didn't really notice the delay and compute it until 1 cycle after the transient happens. So in general, that happens, and what'll happen because of that is that we'll overshoot or undershoot the voltage more than you would in continuous time system, just because of the delay. In other words, this is a nice first order response. We start to dip down here, and we fully recover by, say, 1 millisecond, which this was designed for. So this design looks okay for the digital controller. Now let's check kind of some of the other ones here. So now we have, in this case, we have our Tustin. So this is our Tustin controller approximation, and this is our closed loop transfer function with Tustin. And you can see the pole 0 location actually isn't a whole heck of a lot different than what you saw with the backwards Euler. So that's okay. And the 0 locations, those are actually different than what you saw. You actually have a 0 over here, which is a little bit different, right? You had this 0 here, 0 here. But this is different than the backwards Euler. Okay, so we look at these responses now, and you can see here that we have 3 different responses. So blue, we have the continuous time. In red, we have our this is our backwards Euler. And And in blue here, we have our, whoops, not blue, excuse me, orange/yellow. We have our Tustin. And this goes for voltage, current, and the current command. Okay, it's actually pretty hard to tell any difference when you look at the transient in terms of current. I mean, they all three of them kind of look like they're lined on top of each other, but where you really see the difference in response is the voltage. And here you can see just in this one that the Tustin does a much better job of really kind of converging or approximating the continuous time controller in this case, which is quite interesting. Again, you can look at these delays here. You can see the Tussin actually actuates a little bit faster in terms of delay than the backwards Euler in this case, which is quite interesting. Okay, so what you want to do this is just one design. You can see that it comes back up to 15 volts, and either way these do these. Some people prefer backwards Euler, some prefer Tustin. There's really no hard and fast rule, but what really is important, again, that you kind of go ahead and test these digital controllers as they are and make sure they actually work. And then you also want to test these across load variation and manufacturing variation. For instance, tolerance on L, tolerance on C, tolerance on ESR, and just make sure that these are actually staying stable, responding in the time that you designed for, having the undershoot and overshoot that you designed for, as you vary the process for L, C, R, and etc. So this concludes the digital controller design for the current mode controller of the buck converter. Thank you. All right, thanks. That was the first module today. I'm going to wait about 5 minutes for some questions, and then I'm going to respond to 2 questions from yesterday that I received. So please go ahead, send your questions in as you have them, and we'll go ahead and respond. All right, so I do have a question from Orteza. Will you be talking about measurement filtering, like low pass filter, et cetera, during this course? So I think what you're talking about is filtering of measurements, say like a voltage sensor and or current sensor. Could you clarify if that's what you're referring to? Okay, yeah, thank you. So yeah, this is one of the sections that I don't have written, but I'm in the process of writing. writing. But I think what I'm going to do is tomorrow, I can tell from kind of how the speed of the class is going, I have some extra stuff that is in the process of being developed that I'll go over. It'll be way less formal than what you have here, where you have essentially right now you have video, you have a note set that goes with it, and then you also have homework. But what I'll do is I think I have 4 or 5 modules that I'm in the process of developing that are additional. I have some PLL stuff, some stuff about number systems, and of course, measurement filtering and how that plays into things. So we'll chat about that tomorrow, but in a way less formal setting. Okay, Eric's got a question. Let's see. When would you sample for digital control of current mode control at the rising edge of the gating waveform, etc.? Okay, this is a really good question. So I'm gonna have to go over to my pad here quick. So let me set that up, and I think I can answer this in a better way for you. So. This is actually a fantastic implementation question that is not all that clear unless you've worked in this area a little bit. So it also kind of depends on what processor you use or what company's processor you use. Okay, so hopefully you should be able to see my pad screen now. And what I'm going to attempt to explain is about the gating. When would you sample for digital current mode control? And this is a fantastic question. So this really gets into implementation. So I'm going to talk in response to a processor that we use quite a bit here in my lab for research. So this is a Texas Instruments part, and it's in the Delfino series, and let's see if I can even remember the number. It's like 283779D. I might have an extra number in here, but anyways, it's the dual core Delfino. Now this is going to be a really specific answer, but I'm going to tell you that it really depends on what hardware, what processor, what company you use to implement this. Now, the nice thing with this specific chip and a lot of their TI's chips in the Delfino series and also the Piccolo series is that this part right here is actually on board. This part here and this part here and this part here. So all of this, that was a little messy. All of this is actually sitting already on board the processor. In fact, the comparator is analog. So what happens is in the chip, so here's your TI chip, you have an ADC pin. All you do is you have to make sure you're feeding in the current waveform there. You know, a censored version, right? Of course, it's got to be between 0 and 3.3 volts so you don't break your ADC. But you feed that in there, and that comes directly into this port here of the comparator. Now, you have to do some configuration of this comparator. And that's in there's a module called the CMPSS. I think it stands for comparator subsystem. But you just set up some registers in there, and it'll be readily able to accept this voltage coming here. Now the question is, when do you sample this here? Because this is really your IL star coming from your controller. So this continuously there, it's not digitally sampled. On the chip, that comparator is analog. It's an analog comparator. It's always comparing. But what happens is the input here to the positive terminal, IL star, internally comes from a DAC. This generates IL star. Okay, and so what happens is you can configure the DAC in the comparator subsystem to update at TBR, let's see, TB CTR equals 0. Now, table counter is a counter that counts from 0 to the end of the cycle. So think of it as something like this. It's just a sawtooth waveform. So you can adjust it to set or to update the DAC command at the start of every cycle like this. Okay, and then essentially you're not ever sampling IL. It's a continuous waveform, but what you are, I guess, quasi-sampling or changing only once at the start of the cycle is IL star, the command coming into the non-inverting terminal comparator. Okay, and this command would come after you, or this update would come after you run your controller, so you calculate a new IL star. Okay, and now I gave you a really, really specific answer to this, but as you can see, it really depends on what hardware you end up utilizing to implement your current mode controller. And this, we've done this for other things, not even a buck converter. We've done these for a lot of different topologies, but this hardware is sitting in the Delfino, which makes it really easy to implement. Okay, so hopefully, Eric, I answered your question. If I didn't, please just rephrase. If there's a specific part I missed on, let me know. All right, I'm going to wait a couple more minutes, let's say 2 more minutes, and answer some questions from last time, and then we'll move on. So please send in any questions as you have them. Okay, so clarification from Eric. So it would be at the spike input of the S in the flip-flop. What I would say is it's completely configurable, right? So this would be your S signal, right? And this is setting your SR flip-flop at the start of every cycle. And these are essentially TS with TSW switching length here like this. So you could, let's see, we could write this here like this. So yeah, you could essentially change your DAC command like this, if you will. In fact, this is what we do on ours. We update it at 0, which we're calling, I guess, the start of the set signal. Yeah, that's totally fine. But what I also say is this chip is really configurable. I mean, you could update it at any point, but this makes sense to update it right here because generally then the current wherever you're at is always rising until you hit this point. And it comes, whoops, actually I goofed this up. It'll start rising here until you hit some point. So yeah. It is a really good idea to update right at 0. Doesn't mean you have to, but that's usually when you do it. So good question. Hopefully I answered that satisfactory for you, Eric. Let me know if you have any other questions regarding that. Okay, I am going to address one question that came in over email last night after this current mode control for a buck converter. I think there was a question regarding FC and maybe why the selection of this, etc. This is arbitrary. You're the designer, so this is up to you. I mean, you can make it as fast as you want or as slow as you want within limits and within reason. the faster you go, I mean, ideally in a perfect world, the better, right? You'd like to have infinite bandwidth, which just means that you immediately respond to any transient you see, but practically it's just not realizable with delay and with the transfer function of the plant. So this is a good trade-off between where the plant showed up. Let's see, this would be right around here. In this case, for the current mode control and our switching frequency, which I believe is around 10 kilohertz in this example, and not going too slow. If you go too slow, you're too sluggish. It means you might have a big drop in voltage. Let's see if I did that here. Yeah, so I mean, this may be unacceptable for your design, this much change in voltage. So, I mean, there's a couple things you can do. One is speed up the system, which means you need to get IL up faster, right? If you get it up faster, then VO would dip less. And you may have a spec on this delta V here. You know, you always want it within 100 millivolts of 15 volts. You may want that. And if you do, then you have to have a faster system. It just means that your current's got to get up faster so your voltage doesn't dip, which means if you want your current up faster, you got to have a faster loop. In general, when going faster, it gets more challenging. The closer you get to the ESR 0, et cetera, you got to make sure that's not going to move on you a whole lot with load. So you're going to want to check this. But this is part of being the designer. Just for this example, I arbitrarily selected this. You definitely could select different values and take a look at the responses. But for sure, if you increase it, let's say you go to 2000 hertz, what will happen is IL will come up quicker like this, VO will dip less, and you'll have less delta V if you have a faster loop. So hopefully I answered that question. That came in yesterday over email. And I have one more question that came in last night. These are pertaining to the lectures 3.1 and 4.1. How did you simulate a closed loop system to generate the load regulation? So I simulated it in Plex. So I have no problem giving the models. I have to talk to Professor Mohan and see how he wants to disseminate those to you. Plex is great. It's a great simulation tool. If you don't have a license, that's okay. You can run the model for an hour and then the program will quit and then you can just reopen it again. So definitely enough time for you to run the model and play around with it and see how it works. So let me talk to Professor Mohan in the break and figure out how I can get the Plex models to everybody. Okay, thanks. I'm gonna wait about one more minute, and if you have more questions, please send them. Okay, Eric, thank you for the question. Let's see. Is it practical to implement the current loop digitally by sampling the current? I'm not quite sure what you mean by this. It's definitely practical. It's done. It's done a lot, actually, in high power systems. I'm trying to understand as opposed to using a comparator. Oh, so you want to sample, you want the input to the inverting terminal to be a continuous digital sample of the current. Yeah, I think, let me switch over to the pad again. I think I understand your question. Yeah, sampling current with A to D. Okay, I got you. I understand what you're asking. Let me switch quick to the pad here and see if I can answer this. Okay, so the question now is if we had, whoops, if we had a system like this, where this was IL star coming from a DAC, just like before, but this was coming from an ADC, which is the actual IL. Now, what would happen? Well, let's see if we can sketch this out. So instead of having a ramp current, because we're actually continuously having the signal, you'd have something like this. So to overlay them, we'd have something like this. And then if the switch hit the level, we'd get something like this. And so on and so forth. So that'd be IL, and then that would be one cycle. Here would be the DAC command. And then this would go on indefinitely, right? So this is the question. Would it be practical to do something like this? So, I mean, practically, can you do this? Yes, but the point that is really gonna make you probably not do this, yeah, getting rid of the comparator, is that the ADC frequency got to be much, much greater than the switching frequency. Okay, and this is, I should insert sampling here. So like, let's say you were switching at, I don't know, 10 kilohertz, right? Even sampling at 100 kilohertz is probably, in my opinion, too slow because you're only going to sample 10 times in one period. Going to a megahertz, now you got 100 samples in one period. Okay, that's getting better. Now, if we go to 10 megahertz, you're getting 1,000 samples per switching period. But a 10 megahertz ADC, that's going to be expensive, and setting that up is going to be challenging. And I think cost prohibitive compared to using an analog comparator that's built in. So practically, can you do it? Absolutely. You absolutely can do it. But I think, like, for instance, all these even Microchip, I didn't talk about, has this same type of system that TI has in there. And I believe Infineon, some of their stuff has the same deal, and as well as ST Microelectronics. So I think, I mean, if you just kind of look at the industry perspective, what they're selling to their customer has this. So can you practically do it? Yes. You probably wouldn't see any discrete version of this in the field. Not that there isn't one, but I would venture to guess that in high volume, you would not see this. You would definitely not see it. You'd see some sort of integrated approach like we have here with the Delfino or some of the Microchip series, their DSP series. But yeah, so it's a great question, very good question, and you can practically do this. So you probably want a comparator there anyway, so you could handle time critical events like short circuits. Yeah, absolutely. You know, this goes into another good question, but you can definitely have a trip event off of too high of a current based upon an analog comparator there. You definitely can. And also sometimes it depends on how you design your system. So that would be kind of a software level trip. So even if you had that trip, your processor would have to generate an interrupt, and an interrupt, you have to service it, and there'd be some time there. and then you'd have to do something like shut the gate off. You can also do the protection all the way at the device level, like the gate drive level. As soon as you sense it, analog, shut it off. So you definitely could do that in software. It just be wary that it's a little bit slower than having like a gate level protection where the gate that's driving it, whatever circuit there, senses it immediately, shuts it off. There'll still be delay there as well, but not as much as going back to the processor and going through a interrupt and shutting everything off that way. But definitely, yeah, you want to compare it there to handle short circuit stuff as well. All right, good questions. Wait one more minute. If you got another one, let me know, else we'll go ahead and move on. So Richard says sometimes this sort of thing is done in an FPGA. Could you elaborate on what this sort of thing is? I mean, absolutely, you could do this in FPGA. I've done it in an FPGA, but again, you got to have an ADC. So I'm thinking, what's the one? There's one that has an ADC built in. I'm trying to think which one it is off the top of my head. It'll come to me later. There's an ADC. Oh, what is it? Yeah, it'll come to me. So one thing again with definitely you can do the ADC and off of FPGA, absolutely. Just be wary that, I mean, you really got to sample. You got to sample a lot, even at a 10 kilohertz switching frequency. You got to sample a lot more than that in order to get a really good current mode control. And remember also, current mode control is very, very susceptible to noise. So if you don't have a good, clean reading on a signal that's changing very rapidly relative to how you're sampling it, you definitely go unstable quickly. You got some Xilinx parts definitely do. I'm just thinking there's this, I just was talking with an engineer that was designing one with an FPGA, and I'm trying to remember what they used. It definitely wasn't a Xilinx, but it'll come to me later. I'll think about that one more. Okay, yep, subharmonic oscillation, another great question. This is pretty easy to do. Let's see if I get back to my screen here. Okay, so what happens with that is anytime you have over 50%, you have the possibility of doing subharmonic oscillation. So what happens there? This is pretty easy. So there's many ways to handle it. You could do it in software. I'm going to give you two answers. There's the one for the TI Delfino, and a lot of other chips have this as well. But what happens is, let's see, here's time TS, and then we have another TS, etc. Let's look at 3 time periods here. So they have configurable in the CMPSS comparator subsystem. They have a DAC command, which you could, in theory, just update every time cycle, right? Just like this. Let's say we did that. But they also have an auto decrementer, which is essentially adding a ramp to it. So what will happen is the DAC command will actually, every cycle of the CPU, start decreasing it. And you can set how long between each value it decrements and how much it decrements by. So you can actually set this in the TI Delfino. And of course, this would reset back up to here and auto decrement. So how do you do this? Well, you can do it on the TI Delfino very easily by setting a couple variables in the comparator subsystem. One value is the delay. Oh, this is actually another point. So this is really configurable. So this is meaning it would start decrementing right away. And so there you have your ramp compensation. Another way within the TI is there's actually a delay. So let me draw this again. It's kind of neat. I hadn't done this before I ran across the Delfino, but there's also a delay variable in there, which means that it'll stay a certain value. It'll stay the DAC command, the original one, for some time and then start decrementing like this. So this is configurable within the CM PSS. So there'll be some delay and then it'll start decrementing. So you can configure that, or you can configure it to just start decrementing right away. So that's configurable. Now the other thing is, if you don't have this, this is part of the CMPSS on the TI Delfino. If you don't have that, what you have to do is essentially write software that updates your DAC command continuously. So I've seen this on some of Ray Ridley's stuff. If you have a really cheap microcontroller, and cheap doesn't mean bad, it just means you're a very cost-sensitive application, you may not have all these extra nice subsystems that handle everything for you in hardware. And so what you have to end up doing is you have to write an interrupt that just essentially keeps decrementing your DAC commands. So I'm writing this more coarse on purpose because generally this has more overhead and you can't update this at the actual clock frequency of your CPU because you have interrupts, etc. But essentially what you're doing is you are updating the DAC command a bunch of times within one switching cycle. You're updating this with a software loop. And all you're doing is essentially decrementing the DAC command in between switching cycles by a certain value. And of course, that certain value can easily calculate how much you need to decrement it by. But yeah, this is done. This is done a lot. It's done anywhere you need more than 50%. Essentially, even if I'm not operating at 50%, I usually put in slope compensation because if you have a transient that you're going from a low load to light load, in general, a lot of converters, the duty cycle will increase beyond 50% just to get you back up there. And even during the transient, I'd like to have a nice smooth response. So I always have this in there. But yeah, this is a great question. You definitely have to have this. And that's how you do it. Let me know if you have more questions on that, Eric, and I can help you answer that. Okay, I think we're not getting any more questions, so I'm going to move on to the next module. Thank you for all the great questions. Keep them coming, especially the practical ones. I really like those. We're talking about how we actually implement in real life, processors, et cetera. Keep those coming. Appreciate those. Welcome. This is Nathan Weezy, professor at Marquette University. This is Digital Control Power Electronics. In this section, we're going to talk about the voltage mode control of a boost converter. In black here, you can see that we have the topology of a traditional boost converter, and in blue, wrapped around it, we have the traditional structure of a voltage mode controller. Traditionally, we measure the output voltage in this structure, we compare it with a reference, and we subtract the two, and we generate an error. That error will be fed into the controller, which we are going to design in this section. that controller will essentially output a duty cycle signal, which will be compared against a ramp, and a appropriate switching signal Q will be generated for the switching signal. In terms of what's going on with the ramp is kind of a constant increasing ramp that repeats every TS, and coming or being compared against the ramp is the output of the controller. That will be D, and of course the comparison of those two will generate our switching signal Q. So whenever D is greater than the ramp, it'll be a 1, and vice versa. When it's not, it'll be 0. And here's how we generate our PWM. This is going to repeat again every cycle TS. Essentially, the frequency of this ramp here will set up the switching frequency. Okay, so we're going to design a voltage mode controller for this. So what we have set up here in our MATLAB script are a bunch of the converter parameters. So in this example here, we're going to boost from 5 volts to 10 volts, which is essentially a duty cycle of 0.5. We'll have 100 microhenry for our inductance, which is here, capacitance of 247 microfarad, an ESR of 10 milliohms. Our max output power will be 10 watts, which will be 1 amp at 10 volts. We'll do 200 kilohertz for switching frequency, and of course, based upon our output power here, we can calculate the load resistance at that, which is going to be, in this case, just 10 ohms. Now, what we're going to do here is, for this next part, is set up the plant transfer function. Now, this is generally derived in the Introduction to Power Electronics types course. Here we're just going to work with the result of it and design our controller based on that. So this is our plant transfer function. It depends on duty cycle. This is much different than the buck, so we actually have some stuff that moves around quite a bit. We have a right-hand plane 0 in the buck converter, and we'll talk about what that means. But we have this first thing we calculate is the effective inductance, and it's a function of the inductance and the duty cycle. That gets plugged into equation or line 20, which is the plant transfer function defined. You can find this in any traditional power electronics textbook. And what we'll go ahead and do is Bode plot this so we can take a look at what the transfer function looks like on the Bode plot. In terms of controller design, this is going to be very similar to what we've done for the buck. With voltage mode, we will have our controller design parameters here. And what these will do are set the gain and phase of our transfer of our controller. And so we can set a bandwidth and we can set a phase margin. And bandwidth is going to essentially tell us, is very strongly correlated with damping, and gain or crossover frequency is very strongly correlated with response time and speed of the system. So what we'll go ahead and do is we will calculate the gain and phase of the plant at the desired crossover frequency. So this is that one point, that one crossover frequency. This is the plant, and we're asking for the gain and phase at that point. Once we do that in this design, what we'll go ahead and do is calculate phi boost. Phi boost is how much phase boost we'll ask from the controller at that point. The controller type will be a double pole double zero with an integrator, so K boost will give us our ratio between the pole and the zero. Line 37 is how much the controller gain we need in order to cross over a gain of 0 dB or gain of 1 at the desired crossover frequency. And once we have that, then we essentially can get the controller gains, which is these lines. And then what I've done down here is just define the controller transfer function based upon the integrator gain, the pole, and the zero. Essentially, this is what we get right here. Okay, so we can pull that out and take a look at that. These are where the pole and the zeros end up. We have a pole at 37,000 radians, a zero at 1,000 radians, and a gain of about 24. All right, so let's take a look at these transfer functions and see if we can make any sense of what's going on. If you take a look at our plant here, this is the plant in blue. In fact, let me go ahead and just outline this here. This is our plant, and you can see that we have a kind of an undamped complex pole there, complex pole pair. Our controller, which is actually shown here in red, Let's see if we can show that here. This is our controller. And of course, if you multiply the two, we designed this for, what do we design this across over for? 1 kilohertz here. We should have a gain. You should be able to see visually a gain of 1 or 0 dB at 1 kilohertz. So here's 1 kilohertz. If we look at the controller, we look at this, you can see these are both equal and opposite in sign in dB, right? So they ought to force the open loop to cross over at that point, which you can see here kind of in this orangish yellow. That is the open loop transfer function. So you can see it does indeed cross over through 0 right here, 0 dB. So our controller is designed properly. Let's just point out where the poles and zeros are here. This should be our 0 location, which was somewhere, what do we say, 1,000 radians. You can see that there. And this is approximately the pole location. You can see where the humps are essentially on our controller transfer function to locate those visually. Now, if we go ahead and close the loop, when we do GCL, you'll see what we have here in purple. We actually come down and we go down a little bit and come up and go down. So this is interesting because the boost is actually a pretty challenging converter to actually try to stabilize, and a lot of that's got to do with the right hand plane 0. So actually, let me go up here to the definition of the transfer function. Here, up here, you see this. This is actually a right hand plane 0. This is up in the numerator, and so what this does is add a little bit of complexity to the design process. So we have another 0. This is the ESR 0. You can see because you have the small r here, and then you have a complex pole pair. And so what a right hand plane 0 is going to do is, so whenever you have some air in your system and you push on it harder, like for instance in the context of a boost converter, let's say your voltage is dipping, right, and you're going to increase the duty cycle in order to essentially bring the output voltage back up. It has the negative effect at the beginning, which is absolutely bizarre to think about. So you increase the duty cycle, get your voltage up, it actually dips more on you, and then after a little bit of a delay, it'll start to come up, and that's essentially what a right hand plane 0 does in terms of the plant. So that can make the design of the controller much more challenging. All right, I think we designed for a phase of about 60 degrees. Let's see if we meet that in our open loop response. So if we look at that, remember this is from 180, so where's GOL? We got it here in orange. You can see that, where are we here? It should be about here, which looks about to be 60 degrees. Now this looks a little goofy because how MATLAB spit out the results for this, but this is indeed a phase margin of 60 degrees. It's just due to the way that MATLAB wrapped the phase on this when we plotted it out. So let's take a look now at a response for this transfer function and this controller. This is in continuous time. You can see what happens here is we have a transient from 10% to 100% load. And what happens here is our output voltage initially dips down and then starts to come up, overshoots a little bit and settles down. In this case, we settled down, and where we have this in seconds, you can see it's about 1 millisecond approximately, so 0.1 to 0.101. It's about 1 millisecond approximately, but just to give you some idea on what the bandwidth is actually doing, if you want this to be shorter, of course, you need to speed up your system, and of course, you overshoot a little bit here. Now, again, this isn't the best design because I'm just arbitrarily picking this frequency right now and this phase margin. So I just arbitrarily picked 1 kilohertz and 60 degrees. May not be the best for this application just because you can look at the end design of the Bode plot and actually you have this kind of dip. Sorry, I'm looking at phase here. You have this dip. You have a gain of 1 here, or 0 dB, and then you dip down and kind of come up over again and then down. You'd like to get that nice and flat, so what you would probably like to do better off is work on damping GOL right here. If you could a little bit, do something with this. That will help quite a bit. You can also relax the constraint on the K-factor approach, so you don't have to put both zeros and both poles at the same location. That's what the K-factor approach does here, so you'd have a double pole, double zero, but you don't have to do that. You could manually start placing them, or you could look at lowering the frequency using the K-factor or increasing the frequency and see if you get better responses and better loop shaping of your open loop transfer function. All right, so actually I'm going to illustrate here too how when you push on the duty cycle right away you get this negative effect. So the voltage starts dipping here and you start pushing on it here, D, and guess what? It keeps actually going down, which is really, really interesting here. This is kind of that right hand plane zero. So all of a sudden your duty cycle is like, oh, I need to go back the other way because that's not working, right? And even here you can see that if this didn't have a right hand plane zero and you were still going down, your duty cycle would actually keep going up. So this is actually quite a very interesting case. And a boost converter, again, is a pretty challenging converter to actually stabilize due to this right hand plane zero. And you really have to have a good understanding of what it's doing and how to effectively make your controller not overact to that, or essentially be stable in the sense of having a right hand plane zero. All right, thank you. This concludes this section on a voltage mode controller design for a boost converter. Thank you. All right, let me know. We'll take questions for the next 5 minutes. As you have them, we'll roll in and we'll go ahead and answer them. All right, Eric asks, what's a good reference for how to compensate converters? Okay, so this is kind of a tough question because there's a lot in this question. So by compensate, do you mean design the controller? I assume that's what you mean. And are you more interested on the plant or just the controller itself? I would say start off with Professor Ned Mohan's our first course in power electronics. And then from there, you can grow into the other ones. I think starting there is a good starting point because it's simple, helps you kind of grasp the concepts. Another good one is Power Electronics by this gentleman from Valparaiso. Just give me 1 second to look his name up. I'm blanking on what it is. Yeah, Daniel Hart. So I'll write it in here. This is another good one. There's that. Let's see. There's also this this is a good one, but I'll tell you this is really in depth. So there's a lot of material in that one. Depends. It can be quite advanced, but that's also a good place to go. And let me think. Controls. There's one more book. Sorry for the pause here. I'm trying to find it here. It's a controls book. So as long as you have the plant, that's the hard part in power electronics. Once you have the plant, I mean, you can use general control theory, your classical control theory to design a controller. I'm trying to think of what's the one. Yeah, so for the plants, yes, state space averaging is where these plants do come from. And it gives you a good model up to about half the switching frequency, which is generally more than enough. I would say if you need to go beyond that, then for me, if I have ever had to go beyond that, I would actually just do the perturb and measure. And you can do that in any simulation package as long as you can perturb D or IL or whatever you're trying to find the transfer function from and to and measure both the gain and phase. So when I want to go beyond that, I generally would hop to like Plex, Plexum, Plex, and just do the perturb, disturb, and measure if I want to go beyond just a state space averaging model. And I'm sorry, I'm taking a little bit of time. I'm trying to find that book. I might have to. Um, okay, it's automatic. This is the one that I'm used to using. I'm not saying it's the best, but uh, it's just a classical controls book for learning controls. So I would say that if you got the plant, you could use any as long as you understand design of general control systems or classical control systems, you can use methods there. So that may be a better reference than just a power electronics book, because what a power electronics book it does really is kind of show you, okay, here's the plant, and then, oh, here's a controller that works, and it just so happens we've been using this one forever, and it works quite well for this type of plant. But kind of the background on all the controls and why you'd use this and the Bode plots and the state space and where to place poles and zeros, etc. That would be more found in like a book like this, Automatic Control Systems. And there's other ones, but there's a lot of controls books out of there. But no, this one's by Ben Koo. Let's see if I got this right. Um, Benjamin Koo, and I'm forgetting the other gentleman's name. What is it? Farid Gulnari, and I'm probably destroying that name. I apologize. But Ben Koo is the gentleman I remember. Okay, I'm going to leave a couple more minutes for questions. Let me know if you have All right, so we have another question about references for digital controllers. Let me put that together. I can't recall off the top of my head. I got 5 books sitting on my desk, and I'm not at my desk in my office at the moment, but I have those, and I promise I will get those to you. I know that there was only one book that literally had digital control and power electronics in the title. And that is one of the books I used. I think it's by Simeon Bousseau. So this was the author, and this was digital control of power electronics. This is a good book. Wait, hold on. Yeah, that's one of them I used. It's a good book. It can be challenging because it's really heavy on the digital side. And I'm trying to think. Yeah, that's the one. So Shrikant has a recommendation on controls. I haven't personally used that one, but there's lots of good ones out there, so make sure you check them out. Yeah, that's the one I remember off the top of my head, but I will get a list of them as a to-do. Yeah, just another book. It just came to me. There were 2 that I remember off the top of my head. But here's the other one by Reagan Zane. And 4 other authors. I think Reagan Zane, Dragan Masanovic, Paslo Montevelli, Luca Corradini. That one I used a little bit too. So I kind of used a smorgasbord of books and material to kind of put this together. Okay, I'm going to start the next module. As always, send in any comments, questions, concerns that you have. Thanks. Welcome. This is Professor Nathan Weezy of Marquette University. This is called Digital Control of Power Electronics, and in this section we're going to focus on the digital controller variant of a voltage mode control of a boost converter. So last time we left off, we had essentially designed a continuous time controller for our boost converter. And now we're going to convert this to the digital domain. And so a lot of the MATLAB code here is the same at the beginning because that essentially laid out our whole controller design. So for instance, here was our buck converter parameters. As we go down here, we're essentially defining the plant. And these are our controller design parameters. And this will be the controller design. So up until this point, this is all the same as the previous section. This is all in the continuous time. And what we're going to do is go ahead and actually take a look at converting this to the digital domain using two different transformations, and also we're kind of going to look at two different rates of sampling, okay, and just to kind of see their effect on their system. So this, remember, let's recall that we had this boost converter switching at 200 kilohertz. So the first thing we're going to try here is a 10 kilohertz controller. So that means we're going to update or make our decisions or update the controller output at 10 kilohertz. In that case, it'd be every 100 microseconds. And what we'll do is we're going to design a couple digital controllers. So we're going to have the backwards Euler. So backwards Euler, that'll be line 5. And all we're doing is using the backwards Euler's approximation, line 4, and substituting that in for S. This min real is just to cancel any zeros or poles in the transfer function that MATLAB does not automatically cancel. And so this line 5 will give us a digital controller in backwards approximation. We'll also look at the variant from zero order hold, which we can just call C2D. It's a nice MATLAB function that'll give us that equivalent. With that approximation, we'll also do the Tustin, which is using that same function, just calling Tustin here, sample time at 10 kilohertz, and we'll have that design as well. So we got a couple of controllers to choose from. Now, not right away, but later on, I'm also going to consider looking at the controller at 50 kilohertz. That means we're switching at 200 kilohertz, so every fourth cycle we'll update our controller. Okay, and we're just going to see the effect of having different rates, because it is going to change your controller quite drastically, and we'll see what that is. All right, so for the first response here, this is actually backwards Euler. And this is at 10 kilohertz. And this is our controller right here. Okay, it doesn't look too bad, except for we have a big transient, and it doesn't look like it's settling down either. So the output voltage is constant, then we have our transient, and we're just ringing. And in this transient, just to be clear on what we're doing, we're stepping from 10% to 100% of full load. And you can see that we're oscillating. Essentially, this is not stable, so this is not good. And all I did was take our continuous time controller and convert it to digital at a sample time of 10 kilohertz and use the backwards Euler's approximation. So this actually illustrates that you can't just number crunch and assume that everything's going to be stable. So this is kind of here to highlight that effect. Okay, so let's take a look at now. This is Tustin at 10 kilohertz. Now you're saying, okay, this looks stable, but actually it is stable. It does converge down back to 10 volts after the transient, but this thing rings way more than what happened with the continuous time response. In fact, you can see here our discrete steps are quite large relative to the switching frequency. So this is our 10 kilohertz update of the duty cycle here. And you can see kind of these straight edge approximations of the current due to that different rate between switching frequency and update frequency. So this rings quite a lot, actually. This is not a desired response, I would say. But just to kind of highlight that you can't just arbitrarily pick a frequency here to do this at. Okay, Let's go ahead and take a look now at this controller design. And what we are at now is this is 50 kilohertz. This is our controller for that. And this is backwards Euler. So I used the same one before as backwards Euler in terms of approximation, but now I'm doing the sample time at 50 kilohertz 5 times faster. And it's still 1/4 the switching frequency. So you can see here is the actual discrete steps in U. This is at 50 kilohertz, while the switching frequency here, which you can see in the current IL, is about 4 times faster. But what you can see here is that we're actually we got a better response. I wouldn't say it's the best response, but it's much better than anything we saw at 10 kilohertz. Okay, let's go ahead and look at now our Tustin at 50 kilohertz. And this is our controller here. And you can see a response here. And you can see this one's probably even better than the backwards Euler, but we're going to compare those all next. So again, you can see the right-hand plane 0. We start actuating up. The voltage keeps dipping. The controller doesn't know what to do because it thought that if you forward actuate, you'd actually bring the voltage up. So it starts swinging the other way, and then all of a sudden the voltage starts to come up again. Now that's again the right-hand plane 0 in action. But we do a good job of actually settling down about 1 kilohertz here. You can see we're essentially in steady state. But we do have a second order response. That's to be expected in voltage mode control. All right, let's go take a look at all these on top of each other. Now I have 5 plots here. You can see blue is our continuous time. So that's the original one we designed in the previous section. Red is our backwards Tustin, which you can clearly see is unstable. Okay, so we can't just arbitrarily pick that. Yellow is our 10 kilohertz Tustin. So you see a big difference between Tustin and backwards Euler at 10 kilohertz. The Tustin actually stabilizes. The backwards Euler is just ringing. And then also you can see our backwards Tustin, our backwards and our Tustin at 50 kilohertz actually mimics the continuous time system pretty well. The only really major difference you can see is in delay. So like for instance over here, here's the continuous time, but here you see the delay in both the backwards Euler and the Tustin. And again, that's to be expected because you have a finite amount of time delay in a digital system. You don't actuate right away, but in continuous time, as soon as you develop an error, you're already actuating. So you can see the discrete differences there. You can also see the discrete differences. This is again 10 kilohertz, whereas in your steps for the 50 kilohertz are much smaller. Now what this is kind of showing, and this is not an end-all be-all for digital controller design for power electronics, but it's showing is, oh, why don't we just sample faster and faster and faster? Okay, yeah, definitely. I mean, the faster you sample, the better you're approximating continuous time to a point. Remember, you do have digital numbers that are representing these. You have fixed point or integers representing these numbers. So in general, you could get into, let's say you wanted to sample at the switching frequency. In this case, it's 200 kilohertz, but you want to design a bandwidth of significantly smaller than that. Let's say 1 kilohertz to 500 hertz. You'd actually have the same problem you have here with the backwards Euler at 10K. You would have this problem because you wouldn't be able to, essentially what you have is a bandwidth or a filter frequency that's significantly far away from your sampling frequency. So 1 kilohertz to 200 kilohertz is a 1 to 200 ratio, or even 500 hertz to 200 kilohertz is a 1 to 400 ratio. And when you get those large ratios between sampling and bandwidth or cutoff, that's where you can have a lot of problems, even without thinking about quantization or integer representation in your number system, etc. Okay, this it concludes the digital controller design for the voltage mode controller. Thank you. Okay, as you have questions, I'm going to pause for about 5 minutes. Please send them in and we'll address those. Okay, we're going to go ahead. We didn't receive any questions and start the next module. Thank you. And please send questions as you have them. Welcome. This is Nathan Weezy from Marquette University. This class is Digital Control Power Electronics. In this section, we're going to talk about the control design for a current mode controller of a boost converter in continuous time. So we have our general structure here in black for a boost converter. We have Vn, the inductance L, C, the capacitance, the output capacitance, R ESR of the capacitor, and our output load resistance R. And in blue, we have our generalized control structure, where GC of S is what we're trying to design in this section, which is our controller. Typical current mode type control, we have a comparator where we're measuring the current and we're comparing that to a current command, IL of star, let's say. So our controller is going to generate the current command, how much current we would like to pass through the inductor. Now, how does this all work? We can generally sketch this out briefly here. We're going to have an S signal for setting, a reset signal, and then we're going to have the output of we're going to have the current command stuff. So what happens in terms of the set signal, that's generated from a continuous pulse generator, which at time TS always generates a small, really thin pulse, let's say less than 1%, and this happens indefinitely. And what that will actually do is generate Q, or turn on the SR latch. So right when set hits, Q will go to 1. Now, how do we actually reset the thing? Well, that is done through the comparison of the actual inductor current and the current command. So here in this green, let's sketch IL star. That's what we'd like the current to be through the inductor, and then in purple we'll sketch IL. So right when we set, we actually are charging up the current through IL, so it'll start linearly increasing until some point it'll hit here. It'll hit the command. Once it hits the command, the comparator will pulse out a 1. In other words, that's a reset because the output of the comparator is connected to the reset. When that happens, the switch will turn off, the inductor will connect to the output. Of course, the current will start ramping out. And this will then again complete a cycle and then start repeating. So the pulse generator will pulse a set and the switch will turn on until IL hits the actual commanded current, and we generate a reset signal, and the switch will turn off and the current will start ramping down again. And so this is the basic structure for the current mode control, using a comparator, SR latch, a pulse generator, and a controller. So kind of understanding that basic block diagram, all we really have to do now is design the controller. Essentially the controller will take the error of the voltage and generate IL star, how much current we actually need. So we're going to talk about all this in terms of MATLAB. This is going to be our boost converter parameters here. And then we're going to define the plant transfer function right here. And where this comes from is a basic power electronics course. And they derive the plant transfer function. We're essentially going to be consumers of that function. We're not going to talk about how it's derived, but essentially we're just going to use it. Let's do some highlights here. If we look at this, we have one pole right there, and up top we have a 0 that's in the right hand plane, and then we have another 0 due to the ESR. So we have an ESR 0. We have a right hand plane 0, which will be tricky to get rid of or work with, and then we have one pole. All right, so this is just, we're going to plot this in Bodie's stuff and take a look at this. This is our controller design parameters here. So we're gonna select our gain, or excuse me, we're going to select our bandwidth, and that will determine where the poles and zeros go. Now with current mode control, we use one pole, 1 0, 1 integrator. So our controller is going to look like line 45. Excuse me, line 45 here. which is our controller. And all the work to design this is similar to the buck converter design, or we're using the K-factor approach. So once we have selected our control design parameters, essentially we need to find where the pole and the zero are, and we do that by getting the gain and the phase of the transfer function at the crossover frequency, which is line 35. Then we calculate how much phase boost we need from the controller in line 36, the gain we need from the controller in line 37. 38 gives us essentially what K boost is. That ratio is how far apart the poles and zeros are to give us the proper phase boost. And then essentially 39 through 43 gives us our controller integrator gain and our pole and zero location. So once we go ahead and complete that, we're going to do that design here quickly. You can run this script, you can copy and paste it. This is what we get for our controller design, or excuse me, I'm sorry, this is our plant given those parameters up above, and this is our controller, the basic structure of it. We're trying to find K, omega Z, and omega P. If you run the script and do the design for this, what you're going to get is one pole, one zero, and one gain. And there is a slight mistake here. These squares should not be here, which is highlighted in line 45. There are no squares here, so that is a mistake. Just disregard that. Those squares are not there. We have one pole, one zero, and one integrator in current mode control. So those are our poles and zeros and gain in line 3, equation 3. Line 4 essentially gives us our pole locations for our closed loop system. And if you look at them, they're all on the left-hand plane, which is something that we generally desire in order to ensure stability. So that's good. So let's go ahead and take our Bode plots and take a look at them in terms of the plant transfer function, etc. GP is our plant. You can see we have a fixed gain. We have our pole, and then we have our two zeros, which is interesting here because what happens with the boost converter in current mode control is the gain actually starts going back up this way, which is really bad because generally at high frequency you want to roll the gain off at least at minus 20 dB per decade so that you don't run into any stability issues. Okay, so we can take a look. We designed this for 1 kilohertz. Our gain, this is about 1 kilohertz here. This was our gain of our plant, and then our controller is this, and you can see that we're centered around 0. So if you add those two together, that'll give you a 0 dB at 1 kilohertz. So that'll force our transfer function, our open loop transfer function, to cross over there, which is this orange. You can see it crosses over right at 0 dB, which is perfect. Now, if you go ahead and calculate the closed loop response, which is GOL over 1 over GOL, you actually see you have a nice damped response. This is probably one of the better responses that we've had. But what you also see here is that the gain drops down to, I don't know, minus 30 dB and then just stays level even up to high frequency. So that's something interesting. It's not continuing to go down like a low pass filter. Something to consider here when you consider the boost converter current mode control. In terms of phase margin, we can take a look at that. GOL, let's see how far we are away from minus 180 here at 1 kilohertz. It looks like we have this distance here, which is approximately 60 degrees, which is what we're looking for. Again, this isn't wrapped properly because of the way MATLAB output it, but is indeed 60 degrees away from minus 180, which is exactly what we'd like. Okay. Let's take a look at the output response of this boost converter in current mode control. Again, we are stepping from 10% step of load up to 100% in this case. And you can see that we have generally a first order response for the voltage, so it starts dipping here. You can see our control actuation goes up here and stays up to this. Remember, this is no longer D, this is actually the current. This is IL star, if you will. This is how much current we'd like to flow. And you can see that IL and the U signal here are tracking, meaning if you lay them on top of each other, the peak should hit exactly where IL star is. So if you have this peak here, it should match this. Okay, the other thing you can see is that this recovers in, let's call it, although this is 1 kilohertz, you'd expect it to be here. It's not exactly there yet in terms of voltage. The current is getting up there, and easily enough time, but response time is more like 2.5 millisecond here before it gets up. But I like, in general, current mode control is more desirable. I mean, not always, but it's nice because you're directly controlling the current, so you generally have a nice first order type response. And generally, unless you make it unstable, you don't have any ringing, which is good in terms of response time. Okay, thank you for taking a look at current mode control of a boost converter. This concludes this section. Thank you. All right, so we're gonna give about 5 minutes here for questions. As you have them, please go ahead and send them in. All right, so we had a question from Eric. Are you using really state space averaging models? I would say I don't have any access to Ridley's material. I've met him and seen some of his talks at APEC and conferences such, and I know he holds all sorts of trainings for power electronics, control, etc. But I'm just using regular old state space averaging. So I don't think there's a name really tied to it, but essentially what you do is when you're in CCM, you have two states. And you're in one state, you're in there for D time, and the other state, you're in there for 1 minus D time, and then you average the two states. So you write a state space for one state space for the second state. You write your matrices A, B, C, D, and you average those. You have two sets of them. You have A1, A2, B1, B2, etc., and you average them from D and 1 minus D, and that gives you the average model. And then in terms of getting the actual transfer function, then you have to do, there's a general solution for transfer functions for a state space system when you have A, B, C, D. But if I remember correctly, it's like the determinant of SI minus, what is it? A or C times B in front, C at the end plus D, right? So that's all I'm using is that general state space averaging model. Hopefully I answered your question. Let me know if you have more or if you need a clarification on that. Very interesting, Eric. Thank you for pointing that out. I am not aware of that model. If you have a reference to that paper or yeah, I'd like to see what was actually added to model. So if you have a reference to a material and or a conference / journal paper, please let me know. I'd love to see it. Thank you. Okay, so thanks for pointing that out. I'll look through his site and see if I can find the reference to the paper on that. I would say, yeah, Bob Erickson's book definitely has a lot of state-based stuff in there about how to average and how you do it. It's very good if you go through the Erickson book in terms of getting just the general state-based models. Okay, I'll wait about 2 more minutes for incoming questions, then we'll go ahead and start. Okay, we're going to go ahead and start the next module. As always, please send in questions. Welcome. This is Professor Nathan Weezy of Marquette University, and this is Digital Control of Power Electronics. This section, we're going to talk about the digital current mode control of a boost converter, and namely what we're going to do is from the previous section, we're going to convert our continuous time controller to a couple different digital controllers and kind of see the difference between them and also look at the type of response that we get from them. So in black here in our diagram, you can see that we have a traditional topology for a buck converter, a boost converter, and we've also modeled the RESR, the resistance of the capacitor, because this generally tends to show up in the plant transfer function. And it's very important to know what that is in order to make the system stable. And in blue here, you have the traditional control structure for current mode control of a boost converter. Now, this is going to pick up exactly where we left off in the previous section, so let's kind of outline what we have in our MATLAB script. These first couple of lines, 1 through 12, are our boost converter parameters. These are essentially your inductance and other parameters for running this converter. Lines 14 through 26, these essentially outline the plant transfer function for a boost converter under current mode control. Lines 30 through 31, these are essentially our controller design parameters. So how much phase margin, how much bandwidth do we want? We can set those here. Lastly here in 35 through 45, we have our controller design. Essentially what this will do is give us a design for a controller. And this is where we left off last time. We had one control design for a bandwidth of 1 kilohertz and a phase margin of 60 degrees. Now we have a next block of MATLAB code, and what we're going to do is kind of convert this continuous time controller to a digital controller. And we're going to do this for 2 different sample times. So line 2 is setting TS to 10 kilohertz. This is one sample time. And line 9 is setting a different sample time, say 50 kilohertz. And we're going to have a couple of different types of digital controllers. So for instance, here in line 5, we'll have our backwards Euler at 10 kilohertz. We'll have a zero order hold in line 6, and in 7 we'll have the Tustin. These all just give us different digital controllers using different types of approximation of the continuous time function. And similarly for the other frequency, 50 kilohertz, it looks like I wrote hertz here, this should be kilohertz. We're going to do the same thing. So you're going to get a Tustin, a zero order hold. So here's your Tustin, here's your zero hold, and here's your backwards Euler. And we're going to take a look at the response of all those. And essentially this MATLAB code, all it does is we define this S back, which is, in this case, that is a backwards Euler approximation of sample time TS. We'll plug that in for S. That's what we do here. You see S back, S back, S back, and essentially we get a controller in the Z domain. And we do this for the other ones, but we're utilizing MATLAB's built-in function C2D, which has a couple different variants of substituting in, for instance, zero hold and Tustin. So in all, this is going to give us 6 different digital controllers, 3 for each frequency. We're only going to look at the backwards Euler and Tustin for both 10 and 50 kilohertz, and we'll go ahead and compare that against the continuous time response. So here first we have our backwards Euler controller, and this is for 10 kilohertz. And you can see here, this is our controller structure. These are the numbers. We have a step load from 10% to 100%, and you can see the output voltage is going good until 0.1 second, and then we have a transient, and you can see it rings quite a bit. It takes a long time to die out. In general, this is not a very good response, but this is just to illustrate that we can't just arbitrarily pick these frequencies when we're going from continuous time to digital domain. In fact, you can see that we have these discrete steps that we're asking for you, and essentially this happens very quickly in terms of current mode control relative to switching frequency. So we're having kind of these discrete steps in IL. And essentially what this is doing is making this system way underdamped, which is not what we want. So let's go take a look now at another variant here. We did Tustin, and we did this at 10 kilohertz. These are the gains for the controller. You can see VL shoots down and then starts to recover, and you can see the response of the output voltage. It takes a while. You can also see, again, here's what we're asking. This is U is our control effort, or in other words, IL star. You're having these discrete steps in IL, which you see both in IL star and IL. So essentially what this is telling me is that we can actually actuate the system faster than we're actuating it now. And of course, this isn't the best response, again, because IL kind of shoots over and then settles down, and VO is taking a little bit longer than it should compared to continuous time. So let's just take a look arbitrarily at 50 kilohertz. So here's 50 kilohertz, and this is for backwards Euler. And here's our controller, and you can see here's VO, comes down, comes and recovers, and now you can see these discrete steps here. Remember, this is IL star, and you can see IL here. So essentially what's happening is we're running at 200 kilohertz in terms of switching frequency, but we're only updating IL star every 4 switching cycles, right? So common factor of 4, and you can see that here. But now we're approaching, even at 50 kilohertz, which isn't 200, we're approaching what the continuous time response looked like. Okay, so let's look one step further, and let's look at the Tustin at 50 kilohertz. And you can see, ooh, this is almost the best one of them all. Essentially, the IL star is going right up to what you need. It overshoots just ever so slightly. You can see that both in IL and IL star, but it settles down pretty well to what the load current should be in steady state, and you can see that the output voltage recovers pretty nicely in a first order response. Of course, we could make this faster in time if we wanted by just increasing the bandwidth, but it just depends on your application, depends on how much voltage dip you can sustain, and the application generally drives this. But yeah, this is a pretty good response for Tustin at 50 kilohertz. You would get a slightly better one if you went up to 200 kilohertz, and you may be wondering, why don't I just do everything at the switching frequency? That's great. It depends. It depends quite a bit on cost and the application. So essentially, sometimes you with all the other overhead with communication and the other things that your controller may have to do in terms of being a digital controller for power electronics, you may have a lot of overhead relegated to communication, right? Modbus or whatnot, UARTs communicating. So you may not have the time slices available essentially to run your controller every cycle of 200 kilohertz, or you may just be in a low cost application where you can switch at 200 kilohertz. You can make your components much smaller, your L's and C, your passives, but the digital controller is just not that fast. The PWM can be that fast, but the computation speed is not there for you to update at that. And this is pretty common. You see this a lot in motor controllers. You may be switching your this is low power motor controllers. You may be switching at let's say 50 kilohertz for a low inductance machine, or 75, or maybe 20, but your update rate for your controllers may be orders of magnitude smaller, or integer multiples smaller. So you may be updating at 10 kilohertz or 5 kilohertz for your current controller or for your torque command. So it really just depends. It depends on the application. Essentially, you have a multi-rate system. So you really gotta take a look at these controllers and look at them after you convert them in the digital domain, both in sim and in practice, experimentally, to make sure that you've remained stability. You've contained stability or you've kept the stability from continuous time to digital time. And this gets even more exasperated if you go to really cheap controllers where you may only have 16 bits, for instance, to represent all these numbers, and then it becomes a lot more challenging to design these because quantization kicks in, and that can make you unstable in a very big hurry. So thank you for taking a look at this digital control of a boost converter for current mode control. I'm Nathan Weezy. Thank you. All right, I'm going to wait about 5 minutes. Please send in questions as you have them. Thank you. So it looks like you're correct there, Richard. We have forgot the last slide. Interesting. So I'll have to go ahead and fix that. Let me go ahead and pull this up here. Okay, so you should be able to see the screen now. So this was just the follow on to that. I'll have to go back and add this to the video here, but we skipped this last slide. Essentially what we're doing here in the last slide is going and showing all the designs on top of each other just to kind of give you a feel for how you should design the stuff and the different trade-offs, etc. So in blue you can see if we had a continuous design, that's what you would have in terms of the response. And then we have 4 different digital controllers. We have a backwards Euler. We have a Tustin, both sampled at 10 kilohertz and at 50 kilohertz. And so you can see, of course, the backwards Tustin really struggles when you go to 10 kilohertz. And you can see that both in the output voltage and the current. And of course, you can see these discrete steps at 10 kilohertz, and you can see the current tracking in there much faster. In general, it's a bad idea I think personally a bad idea to change your command at a frequency that is significantly less than your switching frequency. If you can, it'd be best if you could just update your DAC command at the switching frequency, which is essentially what's happening with the backwards and Tustin approach at 50 kilohertz here. And you can see both the green and purple waveforms for IL pretty much lie in unison with the continuous time control. And of course, you can also see the control effort here for all different 5 variations. If we take a look, zoom in really close, you can see the big delay on our, the difference between our Tustin and our, let me get back over here, between our backwards and Tustin. So you can see that we have a quicker response with our Tustin versus our backwards, but that's just because of the delays in the system. This is essentially one 50 kilohertz time segment. Okay, so essentially this will wrap up, and I'm going to have to go back and add the video for this to this one because I forgot it. I apologize about that, but we'll go ahead and add that. In the meantime, if you have questions about this section, please send them to me, and I'll go ahead and make a note that I need to fix this. So thank you for pointing that out, Richard. Okay, so I am going to go back kind of quickly to a question that we received earlier and kind of just hit on it a little bit. So Eric Mayer had asked about using Ridley's state space averaging models, and he had mentioned there's some material on his website and stuff. And anyways, I went and tracked that down to just try to understand what he's asking here and try to correlate this back to the lecture. And what I'm going to do is just show you a quick example of what I was trying to point out earlier in some of the earlier lectures. So let me go share. I'm going to go ahead and share a window with you that is actually our Plex window. This is some of the simulation software that I use to simulate controls and power electronics. So you should see a model that looks very similar to Simulink. This is just a simple buck converter. But what I'm going to show you is what I mean about finding the transfer function if you don't want to go beyond the simple model. So excuse me, if you want to go beyond the simple model. So you could see for current mode control in the buck converter, I was giving you a very simple model. It was 1 pole 1 0, right? And Eric had pointed out that what if you wanted to go beyond that and model more, for instance, the double pole or complex pole pair that you see at half the switching frequency, which would be the subharmonic oscillation, et cetera. So generally what I do is once I want to go beyond the simple model, I just perturb the actual model and measure the gain and phase of the perturbation. So what I mean is, if you look in this diagram here, I'm going to have a perturbation going into my current controller. That just means a really small signal on top of a DC signal. And what I'm going to do is measure the voltage output, both gain and phase relative to the gain and phase of this perturbation. And I'm going to sweep the frequency of this perturbation, right, and generate this Bode plot. Now, Plex has this great tool that you can add these two blocks here, and it will automate this for you so you don't have to do it by hand. And so what I'm going to do is go ahead and show this to you quick. So what happens is I get a plot like this. All right. Now, in general, if you just use this simple single pole, single zero plant approximation that I gave you, that's valid up to, I'd say, at least an order of magnitude below the switching frequency. So if you were switching at 100 kilohertz, that model would be valid up to, like, say, 10 kilohertz. It certainly would not model the double complex pole pair from the subharmonic oscillation. So let me give you an example. If you plotted this using the transfer function I gave you in the notes, you would get this pole and you would get this zero right here. But then it would just stay flat here. And what Eric is pointing out is you can get a model that has more fidelity, i.e. it will show you what happens better at high frequency, the modeling of subharmonic oscillation, which you can see as this complex pole pair here, this double hump. And that's fine, that's there, and you can use the material there. Oh, you're only seeing the Plex schematic. Well, that's not very good, is it? Okay, sorry about that. Let me get up the plot. I see that I have to click and make sure that I share that window. So let's see here. Okay, so you should be able to see this now. And so let me start the discussion over. If you just use the single pole, single zero plant that I gave you in the notes, which is kind of the way to start. It's a very simple model. You'll get this pole, so you roll off at 20 dB, and then you'll get this zero right here. And this line would then stay flat in the model that I gave you in the notes. And so this model was for, we're switching at 100 kilohertz, so this is about 50 right here, half the switching frequency. And what you can do is you can see the pole action happening here due to the subharmonic oscillation phenomenon. So now I did this using the perturb, disturb, and measure the response method, which doesn't give me an explicit equation. Now, if you go into Ridley's thesis there, which I found on the website, you can get an explicit expression. You can put it into MATLAB, and then you can calculate the plant, and it should lie generally on top of this up until a certain frequency. Remember, these models are a model of the actual system. The Ridley model is definitely better, meaning it gets a wider span of the frequency, but it is also not perfect. But I think it's the most widely used if you want an explicit expression. Okay, so I just wanted to hit upon that. In general, the way I do it is once I go beyond a simple model, I'll just perturb and disturb and get the actual model. Because a lot of times I'll add in other things like optocoupler, and an optocoupler will add in a zero because it's got an output capacitance. So I'll throw all that in there, and then I will just get the control to output transfer function by doing the perturb and disturb. But everybody's got kind of a different way. There's no one right way. It's just there's a bunch of different ways to get to the same solution. So hopefully I hit on that a little bit better and answered that better. Please, if you have more questions about this or this previous presentation, please let me know. I'm going to wait about 2 more minutes and then I'll start the next video. Okay, so we're going to go ahead and get this started now. As you go through, please, if you have questions, please send them to me. Welcome. This is Nathan Weezy from Marquette University, and this is Digital Control of Power Electronics. In this section, we're going to concentrate on the control design for a voltage mode control of a buck boost converter. And specifically, we'll focus on continuous time controller in this section. So shown in black here, we have our typical buck boost topology, and consider that we have an ESR here. That's the equivalent series resistance of the output capacitance. That's going to show up in our plant. That's why I draw that here and why we consider that. Normally we don't consider it just for drawing the waveforms, but for control, it's very important that we consider it. Now in this topology, we're going to measure the output voltage, and in blue we have our control structure. So we'll measure the output voltage here, we'll feed it into a sum block and compare that against our reference. Reference is how much we want the voltage to be. The difference between the two will be an error. That error will be fed into our controller, which we're going to design in this section. The controller will output a D, which is compared against our ramp signal, and out of that comparator will be our PWM, which will go to our switch. And in general, how this is done is you have two signals being compared. So you have the ramp, and you have the control signal from the output of your controller that will come in and be compared against the two. Whenever that output signal of the controller is greater than the ramp, you output a 1. When it's less than, you output a 0. And so you get something that looks like this when you compare the two, with green and blue. And so let's see, this will be our D signal here, and then Q, our switching signal, will be our PWM that will be fed to the switch. This is a general structure for voltage mode controller. Now, what we're going to do is we're going to go ahead and design. I got some MATLAB script below here, and we're going to go ahead and try to tackle designing this controller. So first things first, what we're going to do is define our controller parameters, our converter parameters. This is for our buck boost converter. And so in this case, what we're going to have is an input voltage that is 10 and an output voltage that is 10. And in the classical buck boost in CCM, that is a duty ratio of 0.5. Now this could be for an application where your input voltage can move in between your output voltage. So let's say you needed 10 volts, but your input could be anywhere from 8 to 12. This is a good application of that. And also this is going to be inverting, so don't forget that. An inductance of 100 microhenry, output capacitance of 247 microfarad. We'll have an ESR of 10 milliohms, an output power of 20 watts, a switching frequency of 200 kilohertz, and the output resistance will be VO squared over PO. This is at full load, of course. We know that we're outputting 10 volts and we've got 20 watts, so IO is going to be 2 amps in this case. And in order to get 2 amps, R will be 5 ohms. And this is just to emulate the max or full power load resistance. Okay, next what we're going to do is define our plant transfer function, which we do in lines 17 through 25. So this is going to be our plant transfer function. Specifically, the transfer function is defined in 21, and you can see it. So it's kind of a little bit hard to see, but let's kind of sketch it out here. All through here we have the poles. And up here we have our zeros. And you can say that this one right here is due to the capacitor ESR, because this small r shows up in it. And this one right here is due to the effective inductance and the duty ratio. And you can see that these two terms right here. So duty. It's due to the duty ratio and effective inductance. What is the effective inductance? Well, what that is defined up here. Again, that's a function of duty cycle. So 13 defines the effective inductance. Now this transfer function here we're just using. We just grabbed it. It seems if we pulled it out of nowhere, but this would be introduced into an intro power electronics course. You can search a traditional power electronics book on the derivation of this plant transfer function. But this is from D to VO. So we're going to do a K-factor approach design, and so lines 30 through 33 are going to be the controller design parameters. And so we have right here our bandwidth, and this one is our phase margin. And the next section of lines here, we will actually design our controller based upon our controller design inputs or parameters. So in other words, we're going to find the pole location, the zero location, and the controller gain. And lastly, 46 will output the actual controller as a transfer function in MATLAB and take a look at. Okay, so if you plug in all these parameters, 2 through 13 for a buck boost converter, and you take a look at a plant, this is the plant that you would get for that transfer function for a buck boost converter with those parameters. And this is our plant. So that's the process we're trying to control. Here's our controller now. And you can see that, again, this has got a double pole and double zero at the same spot with an integrator gain. This is classical K-factor approach. And here are our controller parameters if you walk through the MATLAB script and calculate them out. Okay, one thing we check just to make sure we have some nice stability is actually the closed loop poles. And you can do that in MATLAB by just calculating GCL and then finding the poles of this. So this is the GCL poles. This will tell us stability. Everything's in the left-hand plane, so you can see negative here, negative, 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 negative. So you can see that they're all pretty far into the left-hand plane, which means that we should have some decent stability. I don't know about the damping, at least for now, but we should have some good stability. All right, so we designed this for 1 kilohertz. Let's take a look at the gain of our open loop transfer function. In blue, we have the plant. So the gain, I don't know, it's around 25 dB in open loop. And the phase is right around, it looks to be minus 180. Now, what we're going to do, because MATLAB does weird things with phase wrapping, is consider 360 or 0 degrees. So we're almost at minus 180 at 1 kilohertz. So when we design our controller, we need a controller with a gain of, in this case, 1 over this gain that's here. In other words, we need negative dB. So we have here negative 25 dB. So you can see that if we add these two together, we will end up with this gain of 0 dB at 1 kilohertz, which is what we want. Essentially, we're setting our bandwidth here. Okay, and so this was our controller gain at this point, and blue was our plant gain at that point. And of course, now if you look at our open loop transfer function at this point, 1 kilohertz, you can see we should have about 60 degrees of phase margin. That's how far we are away from the blue dot there. Okay, very interesting. That's looking good. Now, let's see. Let's take a look at our closed loop response quick. You can see here in blue, nice flat, and then it kind of rolls down, up and down. But this is going to look very good in terms of a response, because even though this is a little under a gain of 1 right here. We don't have a big resonant peak. It's damped out pretty well, so it should have a pretty good response in terms of the closed loop response here. And so let's point this is GCL, or closed loop response. And our phase margin's good, so let's go take a look at the response of the system to transients. So I've plotted here the output voltage in a step load transient from 10% up to 100% or full load. And in this case, what we should have is, you can see our voltage starts dipping and it starts coming down, and it goes all the way down to 9 and then comes up and recovers. It recovers in approximately 1 millisecond, and that softly correlates to our 1 kilohertz bandwidth. If you look at IL, it goes up pretty quickly and then settles in at the steady state current. One thing I will say here is that you can see the right hand plane 0. Whenever we push the system hard up to here, you can see that if we draw a line straight up, you can still see that the voltage was decreasing as we were pushing harder on U, which is the right hand plane 0. This is what can quickly make control systems unstable. Unlike a buck converter, when you push on it harder, generally the voltage goes up right away. Okay, and you can see this is essentially our duty cycle here. And so we go up and we come down and we recover at 50%. We should recover, since this voltage mode control, at the same duty cycle, because we are indeed in CCM before and afterwards. And you barely see any overshoot here, so we are pretty nicely damped. You could put more phase margin here and have it undershoot less, but just depends on your application. So another thing you could do is you can make this so it doesn't dip down to 9 volts. Let's say you had 100 millivolts. There's other things you could do. You could add more capacitance, or you could make your control loop faster. It just depends on what you'd like to do. They both come with trade-off. Of course, adding more capacitance will change your control loop, but it also adds more cost. And could decrease reliability. Increasing your bandwidth definitely gives you a fast response, but could be proved to be more challenging in terms of trying to stabilize the overall system. Okay, thank you. This concludes this section on a voltage mode control design for a buck boost converter. Thank you. Okay, I'm going to wait about 5 minutes, give some time for some questions, and then we'll go ahead and answer those. Okay, we're going to go ahead and get started with the next section. Welcome, this is Nathan Weezy from Marquette University, and this is Digital Control Power Electronics. In this section, we're going to talk about the digital control of voltage mode control for a buck boost converter. And what we are actually going to do is work on our work off of our previous section and convert the continuous time controller to a digital controller. So a lot of the work from the previous section has been laid down and a continuous time controller has been designed. So let's kind of briefly go over what happened here. We have here in this MATLAB script our buck boost parameters for the application or design that we are considering. In lines 1 through 13, these essentially define all our parameters, ESR, output power, etc. Then we have the plant transfer function. In these lines here, they define it, and you can calculate the Bode plot and find the poles and zeros and all that good stuff on the plant. In lines 30 through 33, essentially what we have here is the controller design parameters. And essentially what we can do is select our bandwidth, which is 30, and we can select our phase margin, and our calculation will be automated with this script for purposes of finding the zero pole and controller gain based upon these parameters. And this right here, these lines 35 through 46 is the controller design. And essentially when these are done running, you'll get the controller design. By line 36, you'll have the pole location, the zero location, and we'll also have the integrator gain. And that's kind of where we ended up last section, was this continuous time controller with a phase margin of about 60 degrees and a bandwidth of 1 kilohertz. Now what we're going to do is take a look at this and convert these to the digital domain. And the way we're going to do this is use our approximations in the digital domain. So we're going to do this twice. So once we're going to try at 10 kilohertz, and another attempt we'll try at 50 kilohertz. And what this is we're creating two different digital controllers at two different sample rates. So one's faster than the other, and just kind of see the effect of the sampling rate of the controller versus the switching frequency of the actual buck boost converter. In our case, we're switching at 200 kilohertz. So this is going to be, for instance, 20 times slower, and this one here will be about 4 times slower, the 50 kilohertz. And for each frequency of the controller, the sampling time, we're going to have 3 different controllers that we're going to consider. Here we'll have backwards Euler, and then we'll also do zero order hole and Tustin, and the same goes for 50 kilohertz. Backwards Euler, we'll just call it BE. We'll have zero order hold and Tustin. So we'll have a bunch of different digital controllers to consider. And what I'd like to say is you can simply copy and paste this into MATLAB and run it and look at what the output of this controller is. So the first controller we're going to consider here is a 10 kilohertz. So this popped out of our MATLAB script, and it's backwards Euler. And the first thing you can notice is that the output voltage is wildly oscillating. There's going to be a transient from 10% of full load to 100% of full load, and that's going to happen at time equal to 0.1. And you can see from this plot that it never settles down. In fact, you can also see the discrete sampling time of the output of our duty cycle here. And so essentially the controller is having a hard time tracking the output voltage due to this transient, because essentially converting this to a controller at 10 kilohertz with backwards Euler has made this system unstable. We've gotten essentially the poles of our system very close to the unit circle. So that's not good. This is not a good design, but just to show you that we can't just blindly, arbitrarily pick a sampling frequency and apply backwards Euler. Now here's the same simulation, except for we're at 10 kilohertz and we're using Tustin approximation. And you can see that in this case, the output voltage does decrease, but it comes back and it ends up settling. And so this one, although not perfectly damped by any means, is stable. It will stabilize, so it goes like this, but it rings a little bit longer. So there's not a lot of damping here. Essentially, we had 60 degrees of phase margin. We had a decent amount of damping in the continuous time. Here, it's just not as good, simply because of the quantization and how far we have 10 kilohertz away from the switching frequency 200 kilohertz while simultaneously trying to track a signal at 1 kilohertz. So this is an okay response, but let's go ahead and bump this up in terms of the controller frequency, sampling rate of that. So here's 50 kilohertz, and this is backwards Euler. And what you can notice now is that the output voltage goes down and comes back up, but then it settles. This is looking very close to what we had for the continuous time response. We don't have that second ring like you can see clearly here in the 10 kilohertz Tustin. You can see it go down again and ring out. It means we're having less phase or less damping. Here we have pretty good damping. Okay, and again, this here is we're in voltage mode, so this is our duty cycle. You can see the discrete steps are now at 50 kilohertz for the duty cycle that we're applying. You can see our current goes up, overshoots a little, and then locks in. So this is looking like a pretty decent response. And again, this is 10% load up to 100% load. So this is, a pretty drastic case in terms of load stepping. So you'd expect lower load steps to essentially have better response, meaning that your voltage, for instance, won't go down as much and won't ring. It'll be more damped. So when we test these, we generally try to test very large steps, because anything less than the large step is going to be better in terms of response time and under voltage or over voltage shoot and under voltage shoot. So kind of lastly here, we have our response for the Tustin at 50 kilohertz. And you can see our controller design here. You can see this one looks even better than the other one. We go down, we come up, we barely overshoot, and then we lock right on in terms of the output voltage. You can see the current overshoots a little bit, then locks into the full load current, which is fantastic. It's exactly what we expect. And this here, U is our duty cycle. It goes up, kind of undershoots, and comes down and settles back down, which is what we expect here. So this is looking really good in terms of our duty cycle here. And so this controller, you could go with 50 kilohertz here. This would work fine. You could also try looking at 200 kilohertz. Some issues would arise there too once you're essentially trying to establish a bandwidth or a filter at 1 kilohertz while you're sampling at 200 times higher. The ratio between the bandwidth and the frequency at which you're trying to sample at is quite high. And sometimes you run into accumulation problems there because you're accumulating over a lot of samples. You have to have a large accumulation size or bit size. So, for instance, 32 bits versus 16 bits. Okay, so this will conclude the digital control design for a voltage mode controller for a buck boost converter. Thank you. Okay, please send in any questions here. I'm going to hold for about 5 minutes, give you time to form some questions, and then we'll go ahead and answer those. So it looks like that video cut off the slide again. I will make sure I go and add that back in. In the meantime, here we're plotting the output voltage, the current, and our control effort for 5 different controllers. Blue, just like previous, is the continuous time controller, and we're trying to replicate that as best we can. You can see, as usual, the 10 kilohertz controllers do struggle. Um, they are both in red and yellow, and that's just because they're not sampled fast enough, and that causes more ringing in the system. And of course, you can see it both in IL and VO here. It's quite a bit of ringing. It doesn't even settle in this amount of time. If you look at both the green and the purple, they're both 50 kilohertz sampled digital controllers, one being the backwards Euler and one being the Tustin. You can see they have pretty good performance, with the Tustin just being a little bit better slightly in the control effort. It's mimicking the continuous time probably in a little bit better fashion than the backwards Euler, but that's to be expected. You can see that both the control effort and the output voltage and the inductor current do settle in a relatively quick amount of time. It looks like in this one we're at around 1 millisecond for settle time. So this looks pretty decent for a design in those, but this is just to give you again a taste of, what's the continuous time doing, what is the sampling frequency of the controller, how does that play in. Of course, if you don't go fast enough, you definitely go unstable or make yourself less stable. Okay, so apologize for cutting that one off again. I'll go back and make sure we add that in. Please send any and all questions that you have. We'll go ahead and make sure we answer those. Okay, we're going to go ahead and get started with the next module. Please follow along, and if you have any questions, please send them my way. Welcome. This is Professor Nathan Weezy of Marquette University, and this is Digital Control of Power Electronics. In this section, we're going to talk about the continuous time controller design of a current mode controller for a buck-boost converter. Shown here in black, you see the traditional topology ideal in an ideal sense for a buck-boost converter. And we've also highlighted the fact that we have an ESR resistance right here. That's actually crucial to model because that shows up in the plant transfer function, and you need to take care of that when you're designing your controller. Shown in blue is our control structure, and in general here, GC of S is our controller, which we're going to design. This block here is our pulse generator for setting the latch every cycle, because this is current mode control. And let's talk about what happens or how this works in terms of generating the pulses for a converter under current mode control. So essentially we're going to have Q, we're going to have S and R. That's our SR latch, 2 inputs and 1 output. And then lastly we're going to have the current, and we're going to have the current command. So let's draw where these are. So this is actually IL coming into this comparator, and the output of the controller is actually IL star, which means that's the commanded current, what we'd like it to be, and we're going to compare that against what it actually is, IL. Great. So what happens with this pulse generator is this is a fixed frequency, small, thin pulse that happens every TS. It generates a small, really small pulse. And what this does is, if you watch where it's connected to, it sets the SR latch every cycle. At the beginning of the cycle, sets it to 1. So what will happen is the output of Q will latch to a 1 at the beginning of each cycle. Okay, now how does it get reset? Well, that is done by the output of the comparator, because that feeds the reset signal. So let's take a look and see how this happens. The output of our current controller will output a command called IL star, and that'll be compared against IL. So what happens is at the beginning of the cycle, IL will linearly increase because the voltage across the inductor is Vin until it hits IL star. At this point is where a 1 is generated at the output of the comparator. A small thin slice of reset pulse is generated, which will turn off the SR latch, thus bringing the current back down in a negative fashion in a buck-boost converter. And at the beginning of this cycle, again at TS, the small pulse generator here will generate a small thin pulse that will set the latch again, which will turn it back on. That would be right here. And the current will start to increase again through the inductor current until it mates IL star. And once it happens again, the comparator will output a small thin pulse of 1, and that will reset the latch, which means it'll go to 0. And so what'll happen is it'll ping pong back and forth kind of like this. And the current will always go up and ramp up to IL star. And that's the structure for current mode control. What we have to do in this type of design is design GC of S, our controller here, to give the right current command IL star. In this example, we're going to consider these parameters for our buck-boost converter. So we're going to talk a input voltage of 10 volts, output voltage of 10, duty cycle of 0.5, an inductance of 500 microhenry, a capacitance of 247 microhenry, or microfarad, excuse me, 10 milliohm ESR, an output power 10 watts, switching frequency of 200 kilohertz, and our output load resistance should be what? Well, we know that with an output power of 20 watts and 10 volts, I/O is going to be 2 amps at max. 2 amps, 10 volts. We should have R of about 5 ohms. Now in these next couple of lines, we're going to define the plant transfer function. This can be found in a traditional power electronics course on the design of or finding the plant. This won't change for CCM in a buck boost converter. Let's note a few things about this. Here we have a RHP, right hand plane 0, that will move as a function of the load resistance, the inductance, and the duty cycle. So we got to keep that in mind in order to stabilize this. We also have another ESR 0 that will show up due to the capacitor ESR. And then in this case, in the bottom, we have 1 pole, which is due to the output load resistance and capacitance and the duty cycle. So we have 1 pole. So we can go ahead and Bode plot this and take a look at it and see what it looks like. In terms of the design process, we will, for the controller, this is current mode control, so we're going to use a K-factor approach, which means we're going to place 1 pole and 1 0 in an integrator. So we'll have our controller parameter design, our controller design parameters, excuse me. And in this case, we are going to essentially pick 1 kilohertz and a phase margin of 60 degrees, which are right here. You can go ahead and try different types of bandwidth and phase margin to see what type of responses you get if you want to try to make a faster controller or slower after we go through this. And kind of these last lines are the traditional controller design for K-factor approach. So we'll find the gain and phase of the plant at the desired crossover frequency. We will determine how much phi boost we need at that frequency in order to push the open loop transfer function up or down to cross where we want. We'll also figure out how much gain we need to do that. And then once we have that, we'll find the ratio between omega z and omega p using K boost. Then we'll find our pole 0 and gain values based upon that. And lastly here, we will just define the controller as a transfer function within MATLAB. Alright, so here's our plant. This right here is our plant. This would be if we use those buck boost converter parameters up there and plug that into the plant, that's what we get. The controller design here spits out these pole 0 and gain. So we have a pole at 20,000 radians, a 0 at about 2,000 radians, and a K or integrator gain of about 6,000. So that's the design of the controller. And these are the poles of our closed loop response once we're actually done. This is just to check stability, of course, negative, 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 negative. Everything's in the left-hand plane, so we've at least guaranteed stability. Okay, we haven't really checked on rise time and damping and all that, but we've gained stability here by checking that. Let's check traditionally our phase or our approach here in terms of designing the control loop through the phase plot. So here's our 2 gain and phase at this point. You can see this is somewhere minus 10 to 15 dB right here. So this is the gain of the power stage at our desired crossover frequency, and of course we also have the angle of our plant at the crossover frequency right there. That's that dot. And what we're doing with red here is our controller. We're trying to design a controller that gives us enough gain and phase at that frequency to cross over there and also to give us the right phase margin. So you can see red coming down at minus 20 dB, flattens off, and then down at minus 20 dB per decade again. So this is typically our controller structure with 1 0 1 pole. So this is GC. You can see this is our pole location. This was our 0 location, and that would correspond with these 2 right here. All right, so if you add those 2 gains together, both the controller and the plant, you can see clearly in orange here that we're crossing over at 0 dB. And furthermore, if you calculate the closed loop response, you can see that we have a nice flat 0 dB. We don't have any bump up here, a resonant bump due to the complex pole pair, and then she just rolls off. The big thing to note here too is that at some frequency the gain stops rolling off. Okay, that's something you want to keep track of at a later point to make sure you don't lose stability. Let's also check phase. If you look at our open loop transfer function, you can see here, this is, consider this 0 and this minus 180 and this minus 360 in terms of looking at this. This is just due to the way that MATLAB's wrapping stuff in terms of the function. One thing I'll note here is that if you look at the closed loop transfer function, or the open loop transfer function from here to here, this is about 60 degrees away from minus 180, which means that we've met our phase margin spec, or what we designed for, which is good. And you can also match that here. This is how much phase our controller contributed right here. So you can calculate what that is, and that plus the phase of our blue, which is here, should give us the orange. So it looks like we have a proper controller design for our current mode control for our buck boost converter based upon just phase at the crossover frequency and setting the bandwidth there. All right, let's take a look at a voltage transient here, or a step load transient. We're stepping from 10% to 100% in our transient, and we're taking a look at the output voltage, the inductor current, and also our IL commanded current here. This is no longer duty cycle because we're in current mode control. This is IL star U, the signal going to the comparator. And you can see in this example, everything's actually really nicely damped. This is actually a really good response as we look at this. This current comes right up, barely overshoots, and then it locks right on. And it does so in a very fast fashion. I mean, we're settled down at least in 1 millisecond or 1 kilohertz, if not before in this case. And you can see IL tracks right up and goes there. That's looking really good. And the output voltage is decreasing, but it recovers up in approximately, let's say, 3 milliseconds here for the output voltage. Now you can make this faster. If you don't like this voltage dip here, you can increase C to help you with that, which will change your transfer function, your controller design, but you can also take the bandwidth and increase that. As long as you can make the system stable, this dip will be less. Okay, this concludes the section on continuous time controller for a current controller of a buck boost converter. Thank you. All right, please, if you have any questions, send them away. I'll wait a little bit before we move on. Okay, I'm going to go ahead and start the next module. If you have any questions, just please feel free to go ahead and send them my way. Welcome. This is Professor Nathan Weezy of Marquette University, and this is Digital Control of Power Electronics. This section, we're going to continue talking about the digital controller for current mode control of a buck-boost converter. Where we left off last section, we have designed this controller, but only in the continuous fashion. In this section, we will design the controller in the digital domain and look at kind of the trade-offs between sampling time and the different approximations from continuous time to the discrete digital domain. So what we're going to design today is our digital controller here, and we'll do that by converting our continuous time controller to a digital controller. So where we left off, again, classically we have this buck-boost converter shown here in black, and the blue is really just the surrounding control structure. And let's just recall how we did the whole design process. Essentially, these lines set up our buck-boost converter parameters. And so this just describes, we were doing input voltage of 10, outputting 10 with 50 microhenry inductance, a capacitor of 247 microfarads, 10 milliohm ESR, output power 20 watts, switching frequency at 200 kilohertz, and an output load resistance of 5 ohms. And what we did down here from lines 27 to 26 is just define the plant transfer function. Essentially, this tells us how the output voltage reacts to small perturbations in inductor current. And then we have our controller design parameters, which are adjustable. And lastly, we ended up last section here, which was the controller design. So once you select, for instance, your bandwidth and your phase margin, you get here and you have your controller design. And what this is essentially saying is that we'll have our pole and zero location and the gain of the controller or the integrator at the completion of line 47. So KC will be selected, FZ and FP, which are pole and zero. Those will be all selected, and we'll have our general control structure here in 47 defined. Now at this point, what we'd like to do is convert this continuous time controller to a digital controller and then implement it and see how the system responds. In terms of digital controllers here, we're going to explore a couple different variants. We're going to do a 10 kilohertz sample time. That means we're going to only update the digital controller at 10 kilohertz or every 100 microseconds, whereas the switching frequency is 200 kilohertz. And then we'll also consider controllers at 50 kilohertz, so they'll update their values at 50 kilohertz, which is 4 times slower than switching frequency at 200 kilohertz. We'll do this for 3 different types. Here we'll have backward dealer. And we'll also do zero order hold and tungsten. And we'll do the same for this other frequency at 50 kilohertz. So we have zero order hold, we have tungsten, and we have backwards healer. And what we'll do is just kind of check out the response to all these different types of transformations and how they respond. So the first response we'll look at is shown for this controller shown here, which is backward dealer at 10 kilohertz. And first thing you can say from the output voltage is this is severely underdamped. But you can actually see it is converging down back to 10 over a really long time relative to our bandwidth. So it's not unstable in the sense that the output voltage is going to oscillate. It's just this is a pretty poor design. We generally wouldn't want, for instance, almost 2 volts of undershoot and a volt of overshoot and significant length of ringing. So although the system would eventually converge back to 10 volts without another transient, this is essentially not a very good controller design. And again, let's just recall we're jumping from 10% load up to 100% load in this example. And you can see the same oscillation happening with IL. It tracks the output voltage. The other thing you can see is our discrete steps of updates. Well, this is done at 10 kilohertz. So it goes without saying here, you can clearly say that we would probably like to update our control at probably a faster rate, and we definitely could. IL has no problem tracking at a higher frequency. You can see that here. And down here in the last graph, this is just IL star. This is what we are commanding for IL, and of course the middle graph is what it actually is. So you see good agreement between them. But just overall, not a very good controller design. Let's consider now 10 kilohertz, but we'll go to a Tustin approximation for designing the controller in the digital domain. And you can see now this one responds a lot better than the previous one, but you still see doesn't look very clean. It's still underdamped. Although it's better than the previous one, this is generally not a great response either. And you can see these discrete steps in the IL current. Again, this is just saying that we could probably update the IL current command faster and still be able to track IL. Okay. So we're underdamped here. We're underdamped here. So let's consider the higher frequency controllers and see if we get any better response. All right, now we're back to backwards Euler, but now we're at 50 kilohertz. And you can see now, you still actually, if you zoom in here because of how fast the current controller is, you can see these discrete steps. They're at 50 kilohertz. You can also see the output voltage dips down way less, only to slightly beyond 9, and then comes back up. So the response is very well damped. Now you may not want this much voltage drop, or let's say maybe you want 100 millivolts or less. Well, there's a couple ways to attack this. You can increase the capacitance, redesign your controller, and you can also decrease your inductance so your current responds faster. So you can decrease this so your current responds faster. You can also increase your bandwidth. So these are all levers that you have to essentially make this drop not so fast. So if you increase your bandwidth, what happens is, if you think about increasing bandwidth, is this IL will go up faster, straighter like this. And the faster this goes up, the quicker we can replenish current in the output capacitance so that you don't lose all this area in terms of charge on the cap. So those are just different strategies for essentially making this transient less affecting the output voltage. And again, this last plot here is IL star, what we are commanding the current to be, and you should see good agreement between these two, the actual and what we're asking for. All right, lastly, we'll do Tustin at 50 kilohertz. Just kind of visually comparing these two, you don't see much of a big difference. This is a almost 1 volt undershoot, and this may not be acceptable for your application. So essentially, again, you're gonna have to increase C, decrease L, increase bandwidth. You don't have to do all these at the same time. You can do them separately. It just depends on. In general, increasing capacitance is okay. It does change your controller. You'll have to redesign it because it changes your plant, but it just costs more, and generally that's not the first thing you attack. Maybe you attack lowering the inductance so you can push the current up faster, make this current rise faster, or increasing the bandwidth. That comes pretty free. You just got to make sure you can stabilize it. Lowering the inductance does come with another advantage. If you lower the inductance, you essentially it should be a cheaper component because it should be a smaller component, lightweight and less material. You also can increase the bandwidth by decreasing L, because you have less inductance, which means you can step this current up. Now, there is one trade-off you want to be aware of. The more and more you lower this, the wider range that you may enter DCM in, and you may or may not want to be in DCM depending on your application. But these are all things you want to consider when designing the controller. This last plot here is the control effort, so I don't really need to cross that out, but the control effort here is really just IL star, what I'd like to command the current to be. So this is just taking a look at 4 different controllers. We did 10 kilohertz and 50 kilohertz, both Tustin and backwards Euler, and looking at their responses. Let's take a look at kind of all 5 of those now plotted on top of each other, and you can kind of see the effect of all these at a moment's glance. So again, this red one was backwards Euler, and this was 10 kilohertz. The other one, what was the other one at 10 kilohertz? It looks like it's kind of orangish yellow. That one would be this one. This was 10 kilohertz Tustin. Even that one, even though it was at the same frequency, that one had a much better response than the backwards Euler. That one rang for quite a bit. Remember, blue is your continuous time response. If we kind of zoom in, the one that, there actually isn't one that really tracks that one all that well, but this blue is our continuous time one. I'd say, I guess green is probably the closest to that. And we don't have to mimic the continuous time response exactly, but just to be aware of that there's going to be differences. So this one seems to track in terms of output voltage the best with those. But even when you go to the digital domain, you can see that you have an overshoot in the inductor current, whereas in continuous time in blue, you see that it's pretty well damped. So that's interesting to know. Considered quantization, so we're not getting great agreement here, but that's okay. And if we factor that stuff in, we'll have a pretty good design. And as is already, these backwards and Euler and Tustin at 50 kilohertz are giving us a pretty decent response, having all things considered. If we look at the control actuation output too, another thing you can see here is that the green and purple waveforms are essentially delayed, and that's just the digital delay that is present in digital systems. So you can see like the continuous time controller starts actuating right away, whereas the digital ones take at least 1 to 2 cycle delay, and it depends on what the sampling frequency is and all that good stuff. So okay, this concludes the design of a digital controller for current mode control of a buck boost converter. Thank you. All right, thanks for watching this module. I'll take any and all questions that we have now. And after, I'm going to wait about 5 minutes. If we don't get any questions or go through them all, we're going to go ahead and break for lunch. So we'll be going to 4. I'm not sure if we got enough material to make it to 4. We will see. My guess is we'll end before 4, and then we'll use tomorrow to go over some of the new material that is not released yet that I'm developing in addition to this. So it'll be pretty informal. Probably make lots of mistakes and all that good stuff, but I have some new stuff that we can go through that should be pretty informational. So Eric, can you please elaborate on what you mean by multiple loop controls with inner concurrent loop? Could you just elaborate a little bit more so I can understand what you're asking? Yes. Have I done this? Yes. If you're asking if this is in the course, I don't have a specific one for this course, but what I will say is if you have a suggestion, there's an area or an application that has this that you'd like to see, just tell it to me either in the chat or you can email me and I can develop something for it pretty quickly. But I would say I would say this actually has 2 loops. It's just that we aren't really here. I don't model the comparator, but the comparator actually is the current control loop, if you will. And there's some really good material on modeling just the comparator by the gentleman at University of Colorado Boulder, Erickson et al. There's some pretty good stuff on that, but yeah, I mean, essentially there is actually an intercurrent loop here. It's just the comparator. I just don't explain the model of it here. Yeah, so with all the controllers, we were regulating voltage thus far. In current mode control, you're just controlling the current to regulate the voltage, if you will. In voltage mode control, you're controlling the voltage to the left of the inductor in a buck converter to regulate the voltage on the right side of it. So they're just 2 different things that you're controlling, both with the same objective to maintain or regulate output voltage. Okay, I'm going to wait about 2 more minutes. Please send some questions, and we'll go ahead and answer those. Can you explain DCM? Sure, certainly. I'll do a short one here quick on a buck. And if you need more, we can talk about, we could probably save it for tomorrow in kind of an open forum session and answer that. But yeah, DCM is discontinuous conduction mode. That's when the current goes to and stays at 0 for a certain amount of time during the cycle. So just give me 1 sec. I'll pop up my thing and explain that. Okay, I think you guys can see my screen. So DCM, let's see here if there was an add-on to that. Whoops, there's a breakout here to that question. Okay, so we're going to go back to Richard's here. DCM, so this just has all to do with IL. And so if you look at a cycle and the current stays at or above 0 for all time during this cycle, and it doesn't matter, this is doesn't matter what the converter is, this is for any of them, as long as this current is greater than 0 for all time, you are in CCM, continuous conduction mode. Now let me give you an example for the buck converter, and this works with the boost and buck boost as well. If this current starts at 0, rises, falls, and then stays at 0 for some time, then you have discontinuous conduction mode. Okay, and so this would be IL equal to 0 for some t. And so this actually gives you a rise to a third state. So this would be more reserved for a classical power electronics course, but this third state is usually when both the switch and diode are not conducting. And so this is generally termed DCM. And again, I haven't really drawn a schematic because it's topology agnostic, meaning this would be the same for a buck, a boost, or a buck boost. Okay, so we have one from Vijay Kumar. While comparing actual voltage with reference voltage and regulating it via PI controller, could it be made to convert the voltage error to current for inner loop regulation, Iref versus Iash? So I think the question is, can we use a PI controller? Okay, so PI controller. Let's just take a look at this from the controls perspective for a second. So this is going to be, let's see, Kp plus Ki by S. So here's your controller, right? You have a proportional gain and you have a integral gain. And so if you combine these two, so you have a rational fraction here, what you will get is something like this. And so what you have, these are the same things, but what you have here is an integrator or a pole at the origin, and you have a 0. So what this means in terms of the Bode plot is that you're going to be dropping off at minus 20 dB per decade. This is happening even at DC because of the pole at the origin, and then you will hit your 0 and you will flatten off. So this is where your 0 is. And in general, this may work, but it's hard if you don't have roll off in your controller, meaning if you don't have another pole to roll off here. And it really depends on your plant, but off the top of my head, it gets really challenging with the PI controller because you're not, I guess it depends where the 0 is, but if you have this in your pass band of your open loop, it's going to be very difficult because you don't have anything to roll off the gain at higher frequencies like you would in like a lead lag controller. So While comparing actual, I hope I'm answering your question. It's a little bit hard because we don't have some context on what topology and what we're trying to control. So it seems a little, it's not a very focused question, but I think it would seem to depend on topology application, and it's pretty hard with this without having a pole somewhere. So like use PI controller for controlling like the current in a DC motor, but the motor has a natural low pass pole, or it has a pole. So that makes stabilizing that system a lot easier. Um, let's see here. All right, so what I'm going to do, hopefully I answered that. I'm going to go take a break for lunch. I'll be back at 1:30 Central. Um, Kumar, if I didn't answer your question exactly, just rephrase it for me. And when I get back from lunch, I'll try to clear up any questions that you have. And that goes for anybody else. If I did answer you, Richard, or you don't understand DCM, let me know and you want some further explanation, we can tackle it after lunch. Okay, so I'll be back about an hour and a half, 1:30 Central. Thank you. Okay, welcome back, everybody. We're going to go ahead and get started here. We're going to move into kind of the PLL stuff. And so if you have questions, please let me know. We're going to get started. And as well as if you have past questions, please make sure you submit those. And if there's something you'd like to see that we're not hitting on too, please give me some feedback. So thanks for everybody being here. We're going to go ahead and get started now. Welcome. This is Professor Nathan Weezy of Marquette University. This section, we're going to talk about digital control power electronics and a single-phase PLL. Now, there are many ways to do a single-phase PLL. I'm going to do one that may not be the best way to do it, but it's probably a better way to learn on the first time of putting together a PLL. Okay, so this right here is a diagram shown of a single-phase PLL. And this one has an interesting way of working. So what's going to happen, we're going to feed in the voltage. We'd like to extract the angle of the voltage at any time, so we're going to use a PLL. So here's Vs in time. It's going to come in as a sine wave. That's Vs. And what we're going to do actually is a really simple comparison. If this value of the voltage is greater than 0, we're going to output a 1. If it is not, we're going to output a 0. Okay, so we're going to turn this sine wave into basically a digital signal, 1 or 0. Think of it as signum of the input voltage, okay? So that'll be the signal coming out of this greater than 0 block, okay? Just a simple square wave. The next block is the PFD. This stands for phase frequency detector. Now this one's going to take a second to kind of understand how this block works. So I'm going to describe it with a simple state machine. This is very easy. In the center of these three states are the output of the PFD. That would be this signal here. Now, it's going to either take on 0, -1, or 1. And what these represent, 0 means stay the same, 1 means speed up, and -1 means slow down. Okay? All right. So how do we get from state to state to state and vice versa? So what'll happen here is if we start in state 0, the way we get to state 1 is if we see a rising edge on the incoming signal. So this would be, say, Vs. Great. How do we get out of state 1? Well, that's if we see, we're in state 1 back to 0. If we see a rising edge of the VCO. Okay, what's the VCO? That would be this line. So the VCO is we're going to have another square wave that we're generating, and we're going to compare that against the square wave from this comparator. And we want these two to lock. In fact, we want them to be directly on top of each other. All right, so let's say we're in state 0. How do you get to -1? Well, if we're in state 0 and we need to slow down, that's going to happen because the VCO actually has a rising edge before the signal. So this going this way again is a rising edge of the VCO. And okay, once we're in -1, how do we get out of it? Well, that's when we see a rising edge of Vs. And that's all this state machine is. It's a very, very simple thing. Okay, these are we transition between the three states. It's all on rising edges. Rising edges of the VCO or rising edges of Vs. And this is a square wave being fed in here, okay? Okay, so what comes out of the PFD? It's going to be one of three values. The PFD will either output 0, 1 if it needs to speed up, or -1 if it needs to slow down. But it's going to be one of those three signals. Okay, that's the very simple phase frequency detector. Now there are other phase detectors. For instance, a multiplier can be used as a good way to detect frequency or phase, but we're not using that in this example. Now the controller can be one of many things, but we're going to do a very simple one here. If you look at this structure, it's a simple low-pass filter. That's all you need. We'll try doing a different one later, but that's all we need. Okay, so what happens is the controller is outputting a signal, essentially that is, let's call it delta omega. this omega C is what we call the center frequency. So that's a frequency you want to try to lock onto. So like if we're trying to lock to the grid here in the US, this would be 60 hertz. Omega C would be. Okay, and delta omega is how far in frequency are we away from the center frequency. And it just depends. If you're actually at 60, this will be 0. You could be plus or minus a very small percentage. You could have like 60.01 hertz somewhere, and that delta omega here coming out of the controller in steady state would be the 0.01 hertz to make up for that, okay? All right, so coming out of this sunblock is the actual frequency that we're at right now. And in order to extract omega, all we do is we integrate. So if you integrate omega, you get theta. This is awesome. Okay, great. This is theta, but if we integrate omega forever, right, and we're locked, this theta just is a ramp. It's increasing. So what we're going to do to wrap the ramp is just take the modulus of it by 2 pi. Okay, so for instance, if we were looking at theta, it would go off into infinity. If we wrap, we just have mod. It'll look like something like this. Okay. Lastly, now, the theta here is this ramp, right? This is the theta, or the angle of the waveform that we're trying to extract. But we need to compare this back with the PFD. So what we do is we simply compare this with pi. So we have a dotted line right down the middle, and when we compare it, we generate a square wave that comes out of there like this. And this is what we would just call the VCO. It's a voltage controlled oscillator, if you will. We can control the oscillation by increasing the output of the controller, delta omega. Okay, so this green waveform is now this signal right here, and it feeds back into the PFD. So what happens is we're going to compare this green signal, which is the output of our VCO, with this red signal over here. We're going to compare those two, and what we want them to do is lay directly on top of each other, because if they do, we are then in a locked state. Okay, so that's kind of the simple description of all the blocks of the system. So how do we get this all to work together? What are the gains? How do we design the controller? All right, so we need to know the transfer function of each block. The phase frequency detector is actually quite simple. You can pull out a textbooks on PLLs and get this out of there, but it's really simple. In this case, it turns out to be 1/2 pi. So it's a straight gain, which is nice. It makes designing the controller very easy when you have straight gain blocks. Of course, our controller is going to be a low-pass filter, and we selected that. So that's just going to be GLF here. This will be our controller, equation 2. We'll pick something else later to deal with it. This summation here does nothing in terms of the transfer function, so we're not going to even factor this in. Or in other words, just assume that this is a constant, okay? It won't change the function of frequency. So GVCO, this is 1/s. This is now our integrator. That's fantastic. That's in our path, so I'm trying to figure out all the gains of these blocks. The modulus, well, this block is 1. We're just wrapping theta, so it's not doing anything in terms of phase. It's not changing the phase, and it's not changing the gain at all. So that block actually is 1, which is great. All right, and lastly, this again right here, this is just the VCO, the greater than pi. There's no gain, or the gain is, this is 1, if you will, but there's no phase shift or anything, and we're just comparing this to a constant to generate a oscillating square wave. All right, so having described all that, essentially what happens is that all the blocks are dumbed down really simple. We have 1/2 pi, that's for the PFD. We have k/s plus omega p, that's a controller, and we have the integrator. Okay. Now, if you wanted, you could put a gain on the integrator if you want. You probably will if you're in the digital domain. You just have to factor that in there. So that's why I wrote it like this. But for this example, we're just going to assume the gain is 1. So we can calculate GOL, which is just going to be 1 times 2 times 3, that equation. And we can calculate the closed loop response, which is going to be this. Closed loop response will equal GOL over 1 plus GOL. And why are we doing this? It's because we want to take a look at the transfer function here. We could do root locus here and place these poles where we want, right, by designing K and omega P of the controller, or the low-pass filter. We could do that. But what I'm going to do here is actually something completely different. I'm going to just set the bandwidth of this transfer function. And how do I do that? Well, you just set the open loop transfer function gain to be 1 at the desired bandwidth frequency. Okay, and so I'm doing that. If I go ahead and calculate that, this is what I get for equation 6. And you can see that the things that I have to play with in this equation is K. Bandwidth I'm going to set, and I have omega p, so I can adjust the pole of the controller and the gain of it, and omega WB is the bandwidth of the controller I'd like to achieve. So essentially I have one equation, two unknowns. I don't know K, I don't know omega p, I have one equation. How do I set another equation? What I'm going to do for this is also set the damping. Okay, so bandwidth and damping. If you look at this, there's damping. It's actually in this term right here. So what I'm going to do is set that up. So the damping here, omega p should actually equal 2 times the damping ratio times square root of k by 2 pi. That should be the damping ratio. And what I'm going to do is I'm going to set as the designer my damping ratio and solve for k and omega p. And so if you look up here at this equation up here, I got k, I got omega p, I'm setting the bandwidth. Okay, and so I'm going to select a damping ratio of 1 and 10 hertz. And you can select whatever you want, but I'm going to select those. And I'm going to solve these two equations, 6 and 9, simultaneously. If I do that, this is what I get for my gains. So K, the gain of the filter, the controller, is that. And the pole location is 258.6. And of course, if I plug those into my controller, this is what I get in equation 11. It's just plugged in for K and omega p. And now I have a low-pass filter, which is acting as a controller. Very cool. Now to check stability and phase margin and all that good stuff in the Bode domain, I'm going to calculate things. So I'll plug everything in. I'm going to calculate the open loop response with that K and that omega p, and I'll calculate the transfer function for the closed loop response as well. And you can go ahead if you want, check these poles here, but this is what I got for the pole locations. You can see, note this, the imaginary parts are extremely small. That's times 10 to the minus 6. So in other words, they're essentially in the Laplace domain or S domain. They are on the real axis, which means they're nice and damped. And then of course minus 129, minus 129. Okay. All right, let's just take a look at the Bode diagrams and try to figure out how this all translates from the transfer functions. In blue, I have the open loop transfer function, and you can see the gain is right here, and then it bends down. So this is the integrator part, and then this is the other pole. So let's see if I can see it here. If you look here, you see how I have an S common in both terms. That's the integrator, and then you have another pole here. So you're coming down at minus 20 dB, and then another minus 20 dB and minus 40 dB. That is your plant, or sorry, your open loop transfer function. And the way I designed this is what I want to do. I believe I picked 10 hertz. So I'm going to move this blue line wherever I want it so that I crossed over right here. So what I'm doing right now is verifying that the K and the omega p I picked make the open loop transfer function cross over a gain of 0 dB at 10 hertz, which it does. You can see here's 10 hertz and it crosses through 0. If I do that, then I've obtained my goal of having a bandwidth of 10 hertz, which is what one of my design criteria. Now the other one was damping, which will be a little bit hard to see in the Bode plot, but I'll try to do my best here to describe the damping. Okay, so what I did then is I calculated, oh, you can see my low-pass filter, which is just this right here in red. So it should be a gain, a flat gain, and then roll off at minus 20 dB per decade. That's what a low-pass filter does. If I calculate the closed-loop transfer function, that is here in yellow. And what you can see is the gain from control input to output is 1. That's a 0 dB, which translates to 1. So that means it tracks the reference up until about 10 hertz, and then after that it drops off. So essentially what this is saying is the controller will track a reference as long as it's DC up to about 10 hertz, and then after that it doesn't track as well. It's like a low-pass filter. So the reference is fixed at 60 hertz. This looks nice and stable. Now, the thing with checking the damping factor in a Bode diagram, it should roll off at the pole like directly smooth like this. But if you have less and less damping, what you'll get is a little hump like this. And if you, the more your damping is going towards 0, these spikes will appear at the pole location like this. So visually looking at this right now, you can see it just transitions from a flat gain directly down to a minus 20 dB per decade. It's a very nice damped controller. And again, if it's not damped well at the pole location here, you'll see these peaks like this. Okay, the more significant it, the less damping you have. All right, let's also check something else. If you want to check phase margin, you can check out the open loop transfer function and the closed loop for that matter, and see how much phase you have with respect to minus 180 degrees. So what you want to do is check the open loop gain at the point at which you cross over. We cross over at 10 hertz here. So you can see our phase margin is how far we are away from minus 180 degrees. Let's say this is like 100. So I'm just roughing it out here. This is about 80 degrees of phase margin. So there's a loose approximation. The phase margin is loosely accompanied or correlated, I should say, to damping. So the more phase margin you have, the more damping you have. So 80 degrees of phase margin is pretty good. You know, as you go towards 10, 20, 30 degrees of phase margin, essentially your damping ratio is really low, like 0.1, 0.2, 0.3. So this looks like a pretty decent design in terms of looking at it from the Bode plot. What I've done next is I'm actually going to simulate this whole scheme using this low-pass controller that we have designed, and this is the low-pass controller that I have. Okay. All right, so let's take a look at the plots of the response, and let's explain everything that's going on up here. So up here in blue, you have the square wave. This blue waveform represents me comparing the grid voltage, the sine wave, with 0. So that is the signal I'm trying to lock onto. Red, let's look at red. Red is the output of the VCO. That's what I think the square wave looks like, okay? And what you can note here is at the beginning, we're not locked because these things are not sitting on top of each other, right? And as the controller runs, you can see we're going to be locked. Okay, so let's take a look at what's happening elsewhere. Here's the output of the PFD, second plot here. So what happens is you see we have our first rising edge of the signal, which means that the signal actually happened before our oscillator, which means we need to speed up. So the PFD is saying, hey, please speed up. That's why we get a 1 here. Speed up so that we can catch up to the reference signal. And then what happens is, in time, we catch the rising edge of the oscillator, our VCO, and we go back to a state of 0 at the PFD, which is great. And then a whole cycle goes by, and then look again, we're still a little bit behind, but we got a lot better compared to last time. So the first rising edge of the signal, the PFD will go up to 1, and then we catch the rising edge of our VCO, which is very quickly behind there, and then we go back down to 0. And what you're trying to do is drive this signal essentially to 0. It shouldn't be 1 or -1 for any time when we're locked. Now let's talk about control effort. What happens is, if you look at this right here, we're at 0. This is after the low-pass filter, so the PFD goes into the filter, and the control effort is the output of the filter. So when we get a pulse of 1, it ramps up kind of like this. It's an RC time constant. And then when we go back down to 0, it ramps down, ramps up, ramps down. And what happens is this, remember, the control effort is delta omega, really. That's coming out of the low-pass filter. So delta omega is getting added to omega so that we speed up. And of course, we're integrating that, so we speed up the phase. In fact, you can see it. Here's a constant phase, and then almost we get this blip here. Look at the phase. It kind of, instead of being flat, it shoots up quick to try to catch up. And you can see it a little more down here, too, right there, trying to speed up. And what happens now is over, let's say, 4, 5, 6 cycles of 60 hertz, we're now locked in over here. And if you look down at the phase, we have actually extracted the phase of the incoming voltage, which is awesome because that's what we're trying to obtain. And you can look at the phase is varying between 0 and 2 pi, right? Okay, so let's consider a different loop filter or controller. That was a low-pass filter. Why don't we consider a PI controller, right? PI controllers, everybody uses them. What's the big deal? Why don't we try one of these? Okay, let's try it. So we still have the integrator from, remember that's the integrator to extract the phase from the frequency, and then we have the gain of the PFD. So let's go ahead, calculate our open loop transfer function, which is 16, and then go straight to the closed loop transfer function. So that goes to here and that goes to here. All right, great. So what you can see here in this case, what we're going to do is we have this polynomial in the denominator that kind of sets the pole locations. What I'm going to do here is select a damping factor and natural frequency. So if we look at this, this is the damping and the natural frequency, and this term right here is just the natural frequency. What I'm going to do is set them to what I want, and once I set them, I can solve for Kp and Ki to make the system stable and track. So remember, this term here is omega naught squared, or omega n squared, so I'm going to set that equal here, and this term is 2 zeta damping ratio omega natural. Okay, so I'm going to set that equal to this Kp by 2 pi. And once I set them equal, I'm essentially going to have a system of 2 equations and 2 unknowns. All right, so what am I going to do? I want to have really good damping, so I'll set the ratio to be 1. So that's what I'm going to set zeta to be. And then I'm going to pick a natural frequency at 2 pi 4. That's like 4 hertz. And when I do that, I'm going to solve for Kp and Ki. So I have 18, 19, and 20. I'm going to solve 19 and 20, assuming the damping ratio is 1 and natural frequency is 2 pi 4. If I do that, these are the 2 numbers I get for the PI controller. And of course, I can start calculating things. I can write down this is what the transfer function for the PI controller is. Now I can calculate the open loop, and then I can jump to the closed loop. So open loop to closed loop. And I could take a look at the poles of the system. Here's the poles of the closed loop system, and where do they land? If we look at this again, you can see that we're right here. We have negative values. And look at this. We have really small imaginary terms. That's times 10 to the minus 6. So we're essentially on the real axis, which means we have really good damping. Let's take a look at the Bode plot now. Now in red you can see that we essentially have our controller. You can see it's dropping at minus 20 dB per decade, and then it hits its 0. This is a common PI controller. That's what the transfer function looks like. And of course it should start out at minus 90 degrees, and once you hit your 0, it start ramping up by 45 degrees per decade until it hits 1 decade above where the 0 is, and it rolls off at 0 here, which is pretty common. This is what you see for just the controller part. Let's take a look now. This was our plant. This really didn't change. Excuse me, this is in blue, the closed loop response. If you look at it, I am pretty close to where I was last time. It's more like 8 or 9 hertz where it crosses over. So that just means the bandwidth is a little bit smaller. The thing you want to notice here is if you look at yellow, yellow is actually the closed loop response. And what I want you to see, I'm going to zoom way in here, is actually, you see how it's flat here and then it rolls up just a little bit and goes down. Now if you recall earlier when I was talking about Bode plots, essentially what this means is just a little bit of underdamp right here, just ever so slightly, which means the damping ratio is not exactly 1. It's something a little bit below that. But it's not too big of a deal, but just to keep that in mind when we look at the response here. So now we're going to look at, again, at the controller response here for a low-pass filter. First thing let's notice here is we're out of phase right away, right, with the VCO and the input signal. The signal coming from the grid, the rising edge comes first, so of course our PFD rises up to 1, say, hey, speed up, we need to catch up. And then followed right by that by a rising edge of our VCO, which means the output of the PFD goes, whoops, I drew that the wrong way, it goes back down to 0. And then you can see at this edge again it happens. And so we're slowly catching up. The PFD here is input into the controller. This time, recall that it's actually a PI controller. It's not a low-pass filter. So in fact, if you look at the output of the controller, it looks very similar to the PFD, but what you'll note is that the KP gain is quite high because it instantaneously jumps up. And then if we zoom in here really big, you can see there's a slight ramp on this. That's the integration part. So you can see that right now in terms of the controller, the KP is doing most of the actuation in this case. All right, and if we zoom in way down here, you can see after it comes down, you can see that because of the integrator, this value is actually just a little bit higher than this one. So you can see the difference between the outputs of the two controllers. Now, what happens here in this case is because we are a little bit underdamped is right about here, somewhere here, we're pretty close, but guess what happens in terms of the signal? We actually overshoot. Yeah, right, because our damping ratio is not 1, which means what happens here? Actually, our VCO hits first, which means our PFD outputs a -1, saying, hey, we overshot a little bit. We need to slow down, actually. Okay, and then the next edge is the grid, and then we go back to 0. You can see that here. So that's interesting stuff to note here. There's a little bit of a difference. We overshoot, which means we're a little bit underdamped. And of course, you can see actually we're still a little undershot there, and then you can see these edges here. And so that's just a result of the PI controller here. It doesn't roll off at higher frequencies, so we don't have as good of damping as we do in a low-pass filter. But anyways, I hope this illustrates the difference between the two controllers. You could come up with any architecture for the controller here that you would want. You could try just a straight gain because you do have an integrator in the VCO. You could try lead lag. There's lots of things that you could try here. Low pass filter is great. It was very simple and it works very well. And this will conclude the design of a controller for a single phase PLL. Thank you. Okay, so we just went through the single phase PLL video. Please, if you have questions, send them and we will do our best to try to go ahead and answer them. Okay, so we have a question from Jairam. He's asking, he or she is asking, could you please explain what the significance of the center frequency in a PLL? Yeah, no, this is a fantastic question. It's actually quite simple. The center frequency is what you're trying to lock to. And you have a little bit of a plus minus around that center frequency in which you can lock. And then outside that frequency, you can't lock. And so I don't have any of the derivation of that here and what that is. But what it means is, just to give you an example of numbers, let's say you had a 60 hertz signal, your lock band may be 65 to 55 hertz. So even though your center is 60 and let's say the actual frequency is 60.1, you would still lock onto that as long as it's within the lock band. If you fall outside the lock band, then of course the PLL would never lock. But if you think about it in terms of a grid application, I mean, the grid is very tight on regulation on frequency. So you may go a couple millihertz from 50 or 60, depending where you are. That's about it. If you go much beyond that, other things in the grid will actually shut down or collapse or cut out or protect itself long before your PLL will cut out. So yeah, what is the application of a single phase PLL to power electronics? Well, this is quite easy to answer. A very simple application would be a microinverter for solar. So microinverters are just small inverters, usually 150 to 250 watts, let's say, and they directly connect to a solar DC input of a panel, and the other end directly connects to single phase grid. These are fantastic for home applications because you can buy one panel and one inverter at a time, and it allows you to scale your system up and down very easily. So if you wanted 10 panels, you bought 10 panels, 10 inverters, you'd have, you know, a 20 kilowatt system or whatever. So you have the ability to scale with that. So when you're directly connecting to single phase, you need to, of course, lock onto it and inject power. So that would be a pretty simple application of a single phase PLL. Same would be for like a battery charging for an EV, if you're like a level 1 or level 2, you may want the single phase PLL so that you can just have unity power factor on your charger. So solar microinverter is probably the most prevalent one that jumps off the chart straight away, but you can use it in anywhere where you want to control power flow on a single phase application. These are good questions. Keep them coming. If you have more, just let me know. I'm going to wait about 5 minutes and then move on to the next one. Okay, so we have a question about E in equation 14. So give me 1 second, Eric. I will boot up my tablet and roll over there quickly. Yeah, sorry about the audio. Forgot there for a second. Okay, so to address the first question is what's E here? This is sloppy. I copied it out of MATLAB. So this is 2.7 times 10 to the minus 6 J or I. Same with this one, 2.7 times 10 to the minus 6 J or I. So that's just, it's not E the natural, it's just times 10 to the minus 6, okay? So that's that one. Let's see. I think the other question was how sensitive will this PLL be to noise near? Yeah. Okay, Richard, excellent question. So I think you're going to point out kind of the weakness of this one, which is great. But the reason I start with this one is just from a learning perspective. I think it's a little bit easier to learn on. But yeah, you're absolutely right. Let me go back here. So the red is actually our oscillator. This comes out of our VCO, but this blue one is actually generated by this. So what'll happen is you'll actually measure the grid. So you'll have a voltage measurement across the grid, right, like this. And so you will get some sort of sine wave like this. And of course, what you're doing to generate the square wave is just doing, if it's greater than 0, generate a 1. If it's less than 0, generate a 0. So you get some sort of waveform like this, right? If you compare that to 0. Now the question Richard's asking is how susceptible this is to noise. Now you could do some work. So if you just did a straight comparison with 0, yeah, it would be sensitive. It'd be more sensitive to noise. So you might get something like that, whoops, like that around the 0 crossings, right? Because you don't do anything about it. And you definitely could have an issue there. There's some things you can do in order to get rid of this. If you truly wanted to use this in a real application, you essentially need to put a filter here somewhere. and it just depends where you want to put it. You could put it on this. So the first time you have an edge, so this would be like debouncing a switch. If you ever worked on firmware for a microcontroller in a real application, you could debounce. So it just means the first time it goes up, you would hold for X amount of time. So all those bounces would go away, and then you would neglect anything else. And so essentially it's a filter. You could debounce it if you want. Yeah, it just depends on what you want to do. But yeah, it does have some susceptibility to noise, because you could have a voltage that goes like this due to like some SCRs or something on the grid that are creating more than one zero crossing there. So excellent question. Absolutely. In one of my more advanced PLLs, which is we'll talk about tomorrow, it's not fully developed, but I can go through it completely. There's not a note set, but I can walk through the MATLAB. That one is less susceptible to this type of noise. So excellent question. Keep more Yeah, Eric, same thing, right? I mean, you're filtering. So yeah, the answer to that is definitely. It's the same as debouncing. Essentially, that's what a comparator is doing for you with hysteresis. Okay, so we're going to go ahead and start the next video. Keep sending in questions. They've been excellent questions so far. Keep them coming. Welcome. This is Professor Nathan Weezy of Marquette University. In this section, we're going to talk about single-phase PLL using a fixed point Q format for digital control of power electronics. So we're going to use the same PLL structure for a single phase that we used in the first description of this, except for now we're going to implement this with digital controllers and talk about the difference, and also talk a little bit about some MATLAB code I used to generate this. Okay, so the structure is going to be exactly the same, except for our controller is now in the Z domain, and our integrator is, look at that, a backwards Euler integrator. Okay, awesome. Other than that, nothing's different. I will say that we're going to use 32-bit numbers. Okay, so we're fixed point. And the point actually happens to be, in this case, I believe Q21. So the first 21 digits of our number are going to be fractional, and then we'll have 1 bit for 1 bit for sign, and the rest of the bits will be for integer above the sign. Okay? All right. So we designed a controller last time. We're going to use our low-pass filter here. So these numbers are directly from the last discussion using single-phase PLL in continuous time. Now, what I'm going to do is talk a little bit about some of the MATLAB code that I used to generate this. So first thing I did is I cleared everything out and I generated some symbols. So that you need the MATLAB symbolic toolbox to do this. It'll just set S, omega p, k, and p as symbols. I wrote some transfer functions. Of course, GOL is the transfer function, the open loop transfer function for a PLL. I also wrote the closed loop transfer function here so I could see what it looked like in terms of with no variables, and just look to see what it looked like. So go ahead and clear all that out. I took the transfer function of S and set it equal to S. Bode options is pretty nice. What I'm going to do is go ahead and make everything in Hertz, because I like to look at Bode plots in Hertz, and then I kind of set the limit for that. So that's what these lines do, and it's just stored in an ops structure that we can pass into Bode later. This KVCO, gain equals 1, this is the gain of the voltage controlled oscillator. I just have it scriptable. I know I set it to 1 in the previous discussion, but when we go to implement this maybe in a different controller, KVCO may not be 1, it may be 2, 3, or 4. We can just change it quickly here and go through. FBW, this is the bandwidth of my controller. Again, this is a variable selectable if I want to change it to change my controller. Theta is a damping ratio, that's 1, again selectable. Omega is the bandwidth frequency in radians, so it's just 2 times FBW. Again, that's going to be selectable. If you look at A, B, and C, these are just numbers of the, these are the numbers in front of the polynomial in the denominator of the closed loop transfer function. So if you look at the previous lecture, these are what they are. And the reason I write them as ABC is because I'm going to solve the quadratic equation for them so that I can get the gain K and the position of the filter gain omega F for the low pass filter. So essentially you can see K1 and K2 are just the solving the quadratic equation, assuming A, B, and C are the coefficients of the second order polynomial. Now once I solve it, what you'll see is K1 and K2, this one's the one I'm going to use. K2 turns out to be negative, so that doesn't work. Once I have K1, I can solve for omega F. So none of this stuff is new. This is just written in MATLAB, and this is how I solved for K and omega in the previous lecture when I did continuous time. It's just now that you're looking at my script, you can see what I'm doing, how I'm solving it, and also that I'll be able to change again certain things if I want to adjust stuff later. So at this point, at the end of line 25, I actually have the design of my low-pass filter that will achieve a bandwidth of 10 hertz and a damping factor of 1. And what's going to happen now is I'm just going to check some stuff and convert this to a digital controller. So line 27, what this does is create a transfer function object within MATLAB, because S is a transfer function. Omega F and K1 are the gains of our low-pass filter. And what I'm going to do now is go ahead and convert this to a digital controller. This is also adjustable. TS is the sample time. This is when you're on a microcontroller, essentially this is how fast you're running control loop. You're updating the controller every, in this case, 10 kilohertz or 100 microseconds. So you can change this to scriptable. For now, I'm just going to do 10 kilohertz. It's a good update rate. And I'm going to convert these things to digital controllers. So I'm going to create another transfer function, capital Z, which will be the transfer function of Z with a sample time of TS. And this just gives me Z so I can write the transfer function out of other things. You'll see here in a second. So I'm going to define S back as the backwards Euler transformation or approximation. Remember, we had this from a couple lectures ago that we're going to approximate S in the backwards Euler format as this. So that's essentially what I'm doing. I'm creating S back as that. And then what I'm going to do now is I'm going to plug that into the low-pass filter right here. And GC dig backwards will be my digital controller. And then I'm going to do it for a couple other ones just to check some things. So I'll create a zero order hold one. So there's a fancy there's a very fancy command for MATLAB that will do some continuous times to digital transformations for you with some very simple inputs. So you can pass in the function you want to convert, the sample time, and the type of conversion you'd like to do. Well, they don't have all of them. For instance, they don't have a backwards Euler, so I did that on my own. But I'm also going to check the zero order hold and the Tustin, which is one that we've gone over before. So essentially what I have here, line 32, 33, 34, are 3 digital controllers that are all approximations of a low-pass filter. One's using backwards Euler, one's using zero-order hold, and one is using Tustin, or the bilinear transform. Okay, now this next line of code, so essentially after I'm done with this, I actually have my line 32 through 34, I have my controllers designed and done in the digital domain. Now what I tend to do is I have this code directly in C. So what I do for lines 37 through 55, I export these numbers of these controllers directly to C code. I'm going to show you what happens. So if you look at 42 through 45, I'm going to F print a bunch of integers, which are coefficients of my digital filter. Those coefficients are coming from GC dig backward and GC dig Tustin. I'll show you what happens when you run this code. I think it'll make more sense when you see the output. So lines 1 through 4 here are the output of lines 37 through 45, which essentially give me the 4 numbers of my filter for a backwards Euler approximation of a low pass filter with a bandwidth of 10 hertz and a damping ratio of 1. Now look at, you see these numbers, they're quite large, but remember, this number is in Q21. Okay, that's interesting. So if you want to know what this number really is, you take 2151392 and divide it by 2 to the 21, and you'll get the number it represents. And the same goes for all these other coefficients. Okay, so that's fixed point. Now I do it again, I run this, here's the ones for Tustin, so that'd be lines 47 through 55. You can see the coefficients come out a little bit different. Different approximation, different numbers. Okay, again, they're both different approximations for the low pass filter. So I'm going to run the digital controller for both of these filter structures. See what happens. Okay, first one that I'm going to do, let me step back for a second, is the backwards Euler. And if you look at my coefficients here, that'd be these 4 here. That's what this represents. So what I'm telling you here is that for B1, this 2203593, if you divide, here, let's write it down, just a sanity check here to check Q21, 2203593, and if you divide this by 2 to the 21, what this is equal to approximately is 10.51. So that's a coefficient up here. And of course, there is no constant term, so that's why B0 is 0. Okay, so just to give you a sanity check on that. So these coefficients for fixed point Q21 right here are really implementing this controller down here. Okay, cool. Let's take a look at our response here. This is again for the low pass filter. You can see right away we're behind. We're going to catch up. Our PFD is saying speed up, speed up, speed up. The control effort looks almost exactly the same as it did in the continuous time, except for if you zoom in and look here, you can see it's digitized because we are sampling at 10 kilohertz. So we're running the control loop at every 10 kilohertz. So after a couple cycles of 60 hertz here, you can see we're pretty well locked on. Once we get into here, we're just teeter-tottering back and forth. Though the width of this is just one cycle. So we're at 10 kilohertz, it's 100 microseconds. And essentially that means we're in the stable region, or we're stabilized now, locked on. Let's take a look now if we go ahead and run this for the Tustin approximation. So you can see the controller is a little bit different when you look at it. But let's just look at the output. Again, we start with this, we're on locked phase. The PFD is saying speed up, so we're speeding up, speeding up. You can see the control effort is speeding up, and then you can see we teeter-tot and back and forth on the PFD between speed up and slow down, and it's one cycle wide, and one cycle, the cycle length I'm talking about is the sample time, or 100 microseconds. So once again, we are locked here. We're locked from here on forward. From here, this is kind of the lock state. And there's no discernible difference here in terms of looking at these waveforms, whether one's better than the other. They're just different implementations of the same controller. All right, so let's now take a look at the low pass, the PI controller. We did do that. So here's my code. Line 1 through 17 is my code for designing and selecting the gains for the PI controller. Again, scriptical, my damping is 1, my natural frequency is 2 pi 4 hertz. Line 6 and 7 find KP and KI based upon the damping and the natural frequency. And then I generate a transfer function in 8 of the PI controller. Okay, once I have that, again, 10 through 16, I'm just converting the continuous time Laplace domain to digital. Okay, and again, I do the backwards, I do the zero or hold, and I do the Tustin. And they're just, again, different approximations of the conversion from continuous time or Laplace to digital time. All right, again, I have this kind of same code block here. What I'm doing here is, again, from these filters, I'm actually calculating the fixed point, the Q21, the integers you're actually going to have in your C code when you implement this on your microcontroller. It's the same exact code, and you can see here, these are the outputs for both backward Euler and for Tustin. These are the coefficients, and again, if you want to check, you can take these numbers to see what they represent. Just take A1, divide it by 2 to the 21, you'll see what number it represents, and so on and so forth. You can figure out what it represents. These are, again, Q21. Again, I didn't note it last time, but I made Q scriptable, so if you want to change, you don't want to run your controllers with fixed point Q21 numbers, you can change it here, and your coefficients will come out right. All right, let's look at our response here. This will be for backwards Euler here, this digital controller here. And again, these things are represented by these numbers in Q21. And if you take a look at this, remember this is the integrator, the PI controller. So the output right away, we're not locked. You can see here we need to speed up. And the PFD is saying speed up, speed up, speed up for 3 cycles. And then we overshoot. You can see here we need to slow down, slow down, slow down, slow down. And so remember, it wasn't perfectly damped when we look at that example. Speed up, speed up, speed up, slow down. So we overshot a little bit. And then finally over here you can see we're kind of locked. We're teeter-tottering for 1 cycle between the two. An interesting thing to note here is, again, the control effort is looks very close to the PFD. It's because we have a PI. It's not really a low-pass filter. We're not low-pass filtering the PFD output. So you see basically a lot of the K action or the proportional gain showing up and very little of the integral. I mean, it's there, but it's very little. The other thing I'd like to note is these numbers here, 2 and -2, they are times 10 to the 6. Well, why is that? Because we're now working in Q21. So essentially, this number here represents 1, And this number here represents -1 in Q21 format. And the same goes for the control effort. You can see this is times 10 to the 8, and even the phase, this is times 10 to the 6. So if you took this number, whatever it would be, like for instance this number up here, and divided by 2 times 2 to the 21, you would get essentially 2 pi, or 6.28. Okay, so again, that's the fractional representation for that. Okay, lastly, we have our Tustin approximation for the PI controller for our low-pass filter, or excuse me, for our single-phase PLL. Same thing happens again. We have 3 cycles of speed up. We overshoot because the damping's not exactly 1. We need to slow down, and then right around this time here, we're pretty much locked. Again, you can see the control effort here is PI. It's not a low-pass filter. It's a strong proportional gain component, and essentially we lock somewhere after 170 milliseconds or so here in this case. So we're in the lock state over here. Okay, this concludes the section on Q21 format for single-phase PLL. Thank you. Okay, please send any and all questions that you have on this module. I'm going to wait about 5 minutes, answer all questions, and then we can move on. All right, Richard, great question. Why Q21, not Q20, Q23, etc.? Yes, this is a very loaded question that could take a long time to respond to, but this is part of one of my sections that I'm developing. It's really how do you select what Q to run in, right? And so that is a very challenging question, but let me see if I can do it a little bit of justice. And so, okay, cool. So this was done considering a 32-bit number system, okay? So if you consider Q21, what that really means is you're going to have 10 bits for integer. So usually this is written 10Q21, but to be short, it's usually just Q21. This will be fractional. And of course, you're wondering where's the last bit. This is for sign. So hopefully I did my math right. And 1 plus 10 plus 21 should be 32. So what that'll get you, if you take a look at this, in terms of numbers, let's just look at what is the kind of range of numbers that we can represent here. So the smallest number, of course, would be if we just had 1, and that would represent 1 times 10 to the minus 21. And so approximately, just to give you a rough idea, 4.76, 837 times 10 to the minus 7. So if you picked Q21 and you had 32 bits, this would be the smallest number you could represent. Okay, so this gives you an idea. When you're working in fixed point, your point is fixed.
So you'll have a point like this, have either a 0 or 1 here, and this point never moves on you. So this would be times 2 to the minus 1 times 2 to the minus 2 times dot, 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 2 to the minus 21. And then you have 10 digits this way with the sign bit. And of course, either 0 or 1, so this would be times 2 to the 0, times 2 to the 1, times 2 to the 2, etc., all the way up to times 2 to the 10. And so this would be the smallest number here that you could represent. If you want to look at the largest number you could represent, you'd have to put ones everywhere here and calculate what that would be. Okay, so let's do largest. See if I can remember how to do this. So let's see, if we had a 1 everywhere, how are we going to do this? Yeah, so we need 2 times, let's see right here. Well, let's just go largest integer. You could add up all this fractional components, but let's just go largest integer for now. This would be 2 to the 10, right? Excuse me, this would be 2 to 11 minus 1. Okay, so this would be 2 times 1, 2 to the... So the largest number you're looking at is 2047. You could get this up to like 0.999 if you used all the fractional bits. But anyway, so roughly speaking, your kind of min and max is like this. Okay, plus or minus 2048. And then the smallest number you could represent this. And if you look at, what I picked here, if we were doing a single phase application, and we had like 170 coming in as our peak or 240 or whatnot, this would be okay. This would be plenty enough range, both at the low end, this is pretty low, right? And also at the high end, 2048. So there's no hard and fast rule, but you at least want to be able to capture any number that you would think that would show up in any of the math that you're doing or measurements you're doing and be able to accurately represent that. So that would be on the high side. On the low side, I mean, what you got to be able to do is make sure that you could foreseeably sample too fast, such that like if you had any integral action, your integrator may come up with a number smaller than the smallest number you can represent, thus meaning every time you integrated, you would integrate 0, which would be bad. So that's something you want to check. You always want to check kind of the min and max on both ends to make sure that you don't go outside the bounds. Now, I think another part of your question is overflow. I mean, a lot of times overflow can happen with, let's see, did I lose your question? Overflow can happen with addition or multiplication, right? So if you did like 240 times 240, well, that's obviously going to be larger than 2048. So in general, this is why a lot of times the digital controllers try to keep their factors or ratios or numbers around 1 or 2. So they will divide out A0 to be 1. So if you were looking at your coefficients of a controller, if you had something like this, let's see if I can sketch this up quick. B0, Z to 0, and so on and so forth. We'd have down here B A2, Z minus 2. Let's see, A1, Z minus 1. So if you had something like this is your digital controller. This is just a biquad here. Generally, you divide out so that this term here is equal to 1, and that keeps these other coefficients well conditioned, such that when you multiply and divide, you're not doing like 240 times 240. You might do 240 times 1 or times 2 and add it up. But you definitely have to check for that, Richard. It's a very good point. You definitely want to check to make sure that any addition and multiplication you're doing in these filters / controllers will not overflow the number system that you select. And so again, this is going to be a topic of another section that I'm putting together. It's just not complete, but we'll chat about it tomorrow. Hopefully I did a little bit of justice about this, but yes, Richard, you definitely want to smartly select Q and watch for overflow. You can also make everything 1. That helps a lot. Some people design everything as 1, so you'll never get any number larger than 1, but we can chat about that later. So other questions, please send them. I'll wait a couple more minutes, and then if not, I'll start the next module. Okay, so Jose's got a question here. Let me go ahead and unlock my pad here and see if we can tackle this. So this would have been here in equation, how coefficients in equation 3 and 4. Let's see. I think I gotta go back to my other note set. Yeah, coefficients for equation 3 and 4. Yep, let me pop back to this. Oh, wait a second. No, I think I was. Could you clarify 3 and 4? Is that a line in some code? Is that a line in this code? Which page are we referring to? So let me know, Jose, if are you referring to this, or what are we referring to when you say 3 and 4? Let's see. Or do you mean this 3 here? Say equation 3 and 4. Let's see. Yeah, okay. I think this is what you mean. Okay, so how do we get could you explain how you get the coefficients? Oh, sure. Yeah, not a problem. Okay, so let's back up a second. So grade sheet here. Yeah. All right, these coefficients are our digital controller that come from, it's going to be a long line here. Right here. Okay. I know this is in the analog domain, so it's not exactly. So what we do is we actually calculated the two numbers for the low pass filter, which we're calling our controller. So K1 needs to be found and omega F needs to be found, right? It's just a low pass filter. And then what we did was we took this and converted it to a digital. And how did we do that? We used this identity right here, which is just the backwards Euler. And so we substituted for every S, Z minus 1 divided by Z TS. And you can see I call this now the digital controller with the backwards approximation. All I did was replace S with this S back. And so that's what we get for the digital controller. That's how the coefficients are found. You could do it by hand. I was just using MATLAB to help. And so that gives you these coefficients when you do that substitution. Now, I think the same for 4, it's just that this one is done using Tustin. And so that one is done right here. I could change this to be Tustin, right? Z minus 1 over Z plus 1 TS, but I'm just calling this, it's more convenient. It's just a built-in MATLAB function, continuous to digital, and you pass in the transfer function, sampling time, and which approximation you'd like to use. So this line 34 is what gets you equation 4, or in other words, the coefficients. But you could do it by hand just using the Tustin approximation too. You get the same exact numbers. So hopefully that answered your question there. Please send more questions as you have them. I'll wait a couple more minutes and I'll start the next one. Welcome. This is Professor Nathan Weezy from Marquette University. This section we're going to talk about single-phase PLL using single precision floating point for the digital control of power electronics. So we've already gone over 2 other lectures. One is just a continuous time variant of this, and then the fixed point. This one will be the floating point. And I'm going to start with kind of a word of caution with the floating point. I would strongly suggest, if you're using this in a real application in industry, that you make sure that you are using a microprocessor that has a floating point unit. And the reason is quite simple. It's not that you can't do this with a processor that doesn't have a floating point unit, but a processor that has a floating point unit, instructions such as addition, multiplication, etc., can be done in 1 to 2 clock cycles relative to the frequency of the processor. Now, if you're using a processor that doesn't have a floating point unit and you're using floating point numbers in your C code, unbeknownst to the writer most of the time,
When you go to compile, what the compiler is actually going to do is realize, hey, you don't have a floating point unit on this processor, and load a library to do these calculations. And the net result is that, for instance, a simple addition may require 10, 15, 20, 30 instructions just to do one addition. And if you think about it, that adds up pretty quickly because all these filters are a lot of addition and multiplication. And that's just for one filter. If you have multiple, this adds up very, very quickly. The same goes for multiplication, addition, sign, any function that you do on a single precision floating point number. If you don't have a floating point unit, will incur a large penalty. Especially, and the other thing too is if you're making a lot of library calls, unbeknownst to the writer, because you need to jump to make these calls, you're going to incur overhead to jump to these libraries to actually do that. So that adds even more instructions. You got to save the stack, restore the stack, jump, the cache line, the delay line in the cache, the processor needs to get filled up. So you incur a lot of loss of speed and efficiency. So when you're using floating point, make sure you have a floating point unit on your processor in order to reap the benefits. Okay, we're going to pick up where we left off on the other two designs. We're going to use the same low-pass controller, except for being in the digital domain. Same gain here, same low-pass filter structure. Our voltage-controlled oscillator will simply just be a integrator in the discrete variant. What I've included again is some MATLAB code we can go over quickly in order to talk about what I'm actually doing here. So a lot of this is the same, so I'm not going to go over most of it. It's in the other lecture, but this is the gain of the VCO, which is scriptable on line 14. You have the bandwidth, and you have the damping selectable in the script, so you can do whatever you want in terms of selecting that. Equations 18 through 21 will essentially set up for you to solve for the gain K1. So this is the gain of the low-pass filter. And omega F, this is going to be the pole of the low-pass filter. Line 27 just constructs a transfer function object within MATLAB using those two gains, K1 and omega F. And then line 29, we're setting the sampling frequency for our digital controller. 30, we create a Z transform object, Z, with that same sample time. S back is our backwards Euler approximation for S. And what we do is we plug that into 32 and replace that in for our low-pass filter, and GC dig backwards, or line 32, will be our controller digitally for this low-pass filter. And we do that for zero-order Holden, Tustin, in 33 and 34 via the C2D function, which is a built-in MATLAB function for converting from continuous time to discrete time. Okay, now some of the new stuff we have here is line 36 through 52. We're going to convert at least the backwards Euler and the Tustin digital controller to a floating point number representation and have the C code generated for us for those, defining those single precision floating point numbers. What I want to point out here is that GC dig backwards is an object, right? It's a transfer function object. If you hit period numerator and the first cell, that is a vector of all your coefficients of the numerator, and that is the same for the denominator. We can call the denominator object there, and the first cell will have all the coefficients. And then we wrap it with this. This is a command single. What single does is it'll take an input of a single number or a vector of numbers and convert them to single precision floating point numbers, which is exactly what we want for a controller. So essentially this is going to spit out a vector, B coefficient and A coefficient, a vector of single precision floating point numbers that represent the gains that we'd like to have for a digital filter. Now I do the same here in this code down below for Tustin. The only difference here is that I'm passing in Tustin transfer function object instead of the backwards Euler, and I get these coefficients. Now these two lines down here are the output of my two controllers in floating point precision numbers. Generally what I do is when I'm done and I have a good design, I will copy and paste this into my C code, and those are the coefficients for my two different controllers. Depends on which one I want to use, but those are the coefficients in single precision floating point format. We can now take a look to see what the controllers look like. They're going to look very similar. This is the backward Euler low pass filter. Again, you can see a couple cycles right away. We need to speed up, and then pretty much we're locked on. This is like slow down, speed up, slow down. So we're teeter-tottering between two phases, and you can see right away the phase speeds up here, speeds up a little more, and then we're essentially locked from here on out. Okay, this is very similar to Q21. We're just using a different number system to represent it. Our control effort and PFD and phase are now in floating point, which looks familiar. We have 2 pi, which is 6.28 as the peak for our phase. So that looks very familiar to us. Now if we do the Tustin transformation for the low pass, this is what a transfer function looks like. I have the gains in the previous stuff. I ran it again here, a simulation, and essentially we're getting the same thing as we got before. We'll speed up in 2 cycles, and then pretty much after here we are locked. Okay. All right, so now let's check. We're going to go do this again for the PI controller. All this code from line 1 to 16, all this is doing is producing the controller in the digital domain for the low pass filter. These first few lines are giving us our gain and phase for our, they're giving the KP gain and the KI gain for our PI controller. And then down here, essentially what we're doing is converting these to the digital domain using the same code that I've done previously. Here we're going to go ahead and output the numbers for our transfer function in the digital domain as single precision floating points for C codes. We can copy and paste. That's what these two do. One for backwards, one for Tustin. Other than that, the code's the same. These coefficients are much different than the low pass because this is implementing or attempting to approximate a PI or a proportional integrator. You can see the difference between forward or backwards Euler and the Tustin is very small. So the A coefficients are exactly the same. And if we look at our B coefficients, yeah, they're very, very close. So I don't think you're going to note any difference between these two in this case because of how close they are. So if we look at this, there's our controller for the backwards Euler, and we're using backwards Eulers with floating point numbers. You can see right away we have to speed up. Remember, this one's not damped well, so we overshoot. And we got to slow down, slow down, slow down. And then somewhere over here, we're in the lock state. This is very similar to what we've seen before. And we'll check lastly our other controller. This is for the Tustin approximation for our controller. And again, we're using floating point numbers. The result is almost exactly the same. So these are some controllers that work. For this type of implementation, I would just stick with the low pass. You don't need the integrator in this case because you have an integrator in your VCO. But it was a useful thing to do here just to see, what type of control structures do you need for certain types of plants. In this case, there's not really anything to use a PI controller for, and it's really actually hard to damp it because you're adding an additional minus 90 degrees on top of the integrator that you already have in your system. So thank you for your time. This concludes the discussion on the floating point version of the single phase PLL. Thank you. All right, please send any questions as you have them. If I don't have any in about 2-3 minutes, I'll go ahead and start the next video. Okay, so Eric's got a question about a square wave inverter
Or could it be used in a true sine wave inverter? Okay, so here's the thing about those. You don't need a PLL for those two applications if they're only driving load. And so like a square wave inverter is very indicative of like the cheapest inverter that you can buy. If you head to Walmart and pick one up and it's inverting like 12 volts from your car to create like a 170 or 120 RMS, those generate square waves. They're generally like a modified square wave. It's not a pure square wave. But anyways, you get to set your own frequency in the code, right? So you're not trying to synchronize to a separate grid or a separate source. So there, you can just count, right? You have a timer. You don't need a PLL because you're not trying to lock anything. And the same would go for a true sine wave inverter. If you're going from, I'm just using a car voltage as an example, 12 to 120 RMS, you set your own frequency. So you don't need a PLL in that application. You only really need a PLL when you're going to connect to a grid or where there is another source that is definitely more stiff than your source. In other words, that source is really setting the frequency and you can't overcome it. So yeah, good question. Could I show a schematic of how a PLL could be used in an inverter? So what type of inverter are we referring to? Yes, that I can do for you. Okay, so let me share this here. Okay, so consider this. You have an AC source that's like 170 sine. To make this really accurate, 2 pi t plus some theta 1. Okay, great. And you're connecting to it your inverter. There's some grid inductance here. Here's your inverter. For all intents and purposes, your inverter can be considered just a variable source. So let's consider it's like this, where this thing is controllable. So we have VC, we have sine, 2 pi, some omega, which we can select, E plus some theta 2. So what you want to do in a single phase application is you really need to know what is theta 1 minus theta 2. That's really what you're extracting. Or in other words, what is the angle of the grid? And so if you look at this simple example here, once you have the phase from the PLL, you can shift this voltage to the left through theta 2, to the left or right of theta 1. So for instance, if theta 2 were equal to theta 1, how much power flow would you have? You'd have 0, because you'd have the same voltage. Well, and of course, VC would have to be 170, but you would have the same voltage on this side versus this side. So the difference across L would be 0. Now, if you wanted to shift power to the right, what would you do? You would want to make theta 2 greater than theta 1, and then power would flow this way. And the other case, if you want power to go to the left or back into the grid, you would want to make this to be true. And so the only way you can do that is if you have an accurate value for theta 1. So the PLL is going to feed your controller. And a lot of times it's a power controller. You're just pushing power onto the grid or extracting power. Okay, so the next question here is looking for details of how the output of the PLL produces gating waveforms for the transistors. Okay, so this is a really detailed question. Let me see if I can start over here. The PLL doesn't actually generate gating waveforms. That's okay though. So let's see. There's many ways to do this. Let's not do it in the rotational basis. Let's do it like this. So if you have, so let's assume this is V-grid coming in here, and you have properly extracted theta from it. This would be the output of your PLL. Here's theta from 0 to 2 pi. Okay, so here's your PLL. The grid voltage is coming in, and out comes theta. Okay, so the question is, how do I generate gating signals? That's not a problem. So we'll assume the current controller is there already. In fact, you can use the one from the buck converter, just the current part, so the comparator, etc. What you can do then is, so you have theta, you'll pass this into a sine block. So what you'll have out then is a sine wave with a magnitude of -1 and 1. And then what you'll multiply it by is your, I'll call it IL hat. And what this means is you're trying to control the current to look like this. Okay, so what comes out of this is just a multiplication of the two IL hat sine omega t plus theta 1. Okay, so this is now going to go into your comparator or your current controller, if you will. So this is the only big difference here, is that this will go into your current controller and it will generate the proper gating signals for that. Yeah, no, the PLL doesn't output the pulses. Yeah, just all PLLs get you is theta. That's what this is what you're after, theta. All right. Yes, PWM generates the pulses. That's correct. PLL just gets you the theta of the grid voltage. It doesn't, but the PLL requires a control loop in itself to extract theta, but it is not the control system, if you will, for the power converter. But it's a very important piece, though. Yeah. All right, I'll give 1 more minute. If there's more questions, I'll start the next video. Okay, I'm going to go ahead and start this video, and I think this will be the last one for today. I'll answer questions after this. We'll start back tomorrow. I got a couple left, and then we'll go into kind of the more of the free-flowing session, that some of the ones that aren't fully developed.
Welcome, this is Professor Nathan Weezy of Marquette University. This section we're going to talk about the three-phase PLL, phase lock loop. Okay, so here we go. We have a diagram here that kind of describes a simple phase lock loop for a three-phase system. Let's go over all the blocks. So here's the incoming voltages. This would be 3 sampled voltages for 3-phase. And the first thing that they're going to do is go into this ABC to DQ block. And what this does is compute a mathematical transformation. Now the mathematical transformation is actually written down here in equation 4. So what it's doing is it's taking in three values, VA, VB, VC, and an angle. This angle is right here. And it's fed in here, 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 and here. And we calculate a DQ. Now, what is this for people who are not familiar with the DQ transform? What this actually does is a moving or rotating reference frame. So what we'll create is this space vector Vs that represents the voltage, and this thing is going to spin at omega. And what happens is this thing will take on a real and imaginary values depending on where it is in time. So drawn in purple, that's just to the right, it would just have a real value. Drawn later in time, it might be at this angle drawn in blue, and this would have some real part and some imaginary part. Now that's called a fixed reference frame, and that would be alpha beta. Now what we're going to do is rotate a reference frame with that and lock onto that. So this would be our reference frame D, and this would be Q. And guess what? If we lock that reference frame to that rotating space vector, we get the DQ transform. Essentially, that's what we're doing. And so what happens is if you're locked to it, D is purely a real value, right? And Q is 0 because we're locked on that reference frame to the rotating space vector in blue. So having known all that, essentially what we're going to do in terms of control is that we don't really care what D is. D is actually going to be the magnitude of the space vector, but we don't care about the magnitude. What we'd like to do is actually drive Q to 0, because if we drive Q to 0, that means that we are locked, right? That means there's no imaginary component at all. So essentially, Q is our error. It tells us whether we're locked or we're not locked. So we don't have to do any subtraction. We just measure the three voltages. We plug in what we think theta is. We do the transform. And if Q is 0, we're locked. If it's non-zero, we got some work to do to lock. Okay, so that's great. We'll pass that error into a PI controller, which is shown right here. And that's going to try to drive the error to 0. Now, what comes out of this block is really delta omega. How far are we off of the center frequency, which would be this guy? So for instance, if we're trying to lock to 60 hertz, the center frequency would be 2 pi 60, and when we're in steady state, the output of controller would be 0. But let's say the grid is floated a little bit or it's changed, and the grid's at 60.1, or center frequency is 60 hertz. The output of the controller would be 0.1 hertz in steady state, or excuse me, 0.1. That would be the delta right here. Okay, so that's what'll happen there. Now remember, this is omega. This is what we think omega is, right? And we're going to pass this into an integrator in order to get out theta, right? That's the relationship for it. So the derivative of theta with respect to time is the speed. If we integrate, we get theta. Now, this number would obviously shoot off to infinity as time goes on if we're just integrating a constant. So in order to not have any wrapping or overflow issues, we simply wrap it. And that's what we're doing here with the mod 2 pi. So let me explain what's going on with this. Let's use a different color here. Generally what happen is if you're just integrating, this would take off, right, off towards infinity, but we're taking a mod, so what we'll do is just wrap the phase. And we're wrapping it at 2 pi. It's like this, okay? All right, and so this is a complete control block diagram for a 3-phase PLL. Okay, so let's talk a little bit more about how this thing works and how to design a proper controller for it, and how to test it against various cases that we'll see in real life. So here's, again, our controller is a simple PI controller, which we're going to use here. The open loop transfer function is pretty simple. The gain of the integrator is 1 over S. The gain of the controller, again, is KPS plus KI by S. So that's all the same. So let's put this is our open loop. This is our controller. And where do we get this VG from? Well, VG is the gain of this stage right here. That is our gain of the DQ transform. Okay? All right, so we can calculate the closed loop response now that we have the open loop. So just recall that this is going to equal GOL over 1 plus GOL. And the thing to note here is that we have the roots right here of this characteristic equation, and we can go ahead and put those wherever we like. And so that's how we're going to do this design. Again, we can do it a multitude of ways, but that's how we're going to do this design. So we know that, for instance, this term that sits right here is the natural frequency squared. So we'll just set that equal to the natural frequency, which is what we did. Okay, awesome. This term that's in front of S, we know is 2 theta natural frequency, right? So we can plug that all in with equation 8 and get equation 9. So essentially what we have is we have the damping ratio as a function of Kp and Ki. We're trying to find Kp and Ki. Vg is set by whatever the grid we're trying to connect to is. And we also have the natural frequency, which is a function of Ki. So essentially we can design for whatever we would like. So in this example, I'm going to assume that the grid voltage peak is 170. So that would be our Vg. I'm going to assume we're going to design with a damping ratio of 0.7. It's a decent damping ratio. And a natural frequency of 100 hertz. Now, if you select those three values and calculate equations 8 and 9, this is what you get for equation 10 are the controller gains. And now we have a controller fully designed for this three-phase PLL. Let's just take a quick look at it from the Bode plot perspective. This is in blue here. This is our open loop GOL, and you can see that we're crossing through 0 gain, dB gain, or gain of 1 at about 100 hertz. Okay, that's great. So what that's going to tell us is our bandwidth is roughly 100 hertz here. And you can note that by looking at the closed loop response, because this is GCL. Essentially is going to pass anything from 0 up to 100 hertz, and then it starts to roll off. Essentially filters out anything beyond that. You can also look at our phase margin response for the open loop transfer function. You can see we're somewhere around, I don't know, let's see, 135, 130, somewhere around approximately 60 degrees of phase margin. Again, that's how far are we away from minus 180 when we cross through a gain of 0 dB. Okay, so this is a good design. Remember, we're talking about phase margin. The more phase margin, the more damped you are, essentially. All right, so the first thing we do when I ran this simulation for this PLL with this controller is just checked a few things. And what I'm doing here is, this is the D axis. So that's the D coming out of the DQ transform. This is the Q axis. Remember, we want to drive the Q axis to 0. That means we're locked. This is control effort, U. So that's what's coming out of the PI block in order to drive the controller to steady state. This is our phase, or theta, if you will. And these are the three-phase voltages. Okay. What I'm simulating in this is, we start at time 0, we're already locked. Okay, and that's actually pretty easy to see because everything's in steady state. Q is fully at 0. The control effort's not changing. We have a nice fixed phase, and you can see the frequencies of our voltages and phases of them are not changing. But what am I simulating here? I'm actually going to simulate and try to understand what happens to different transients. So what I've actually done here in this example is I have about a 17 volt jump in the voltage at this time. So if you come in and look here at the voltages, they're going along, and then all of a sudden they jump up by about 17 volts. And this is for all three phases. You can see it here, you can see it here, you can see it here. So this is just a simple transient on the three-phase line. And you can see the only effect it really has on the system is that D jumps right here. You can see it. But it doesn't affect Q at all. You can see Q remains locked So we don't have any issues with Q when you have a voltage jump. Now this was a balanced voltage jump, so you're not going to see anything on Q, so there's nothing to expect there. So, okay, this looks good. The controller's keeping track here. Let's check a different transient now. All right, so what are we going to do now? We're actually going to do the response to a phase step of about 0.62 radians at time 0.21. Well, here's time 0.21, and you can see what's happening here. If you look down at these voltages, let's look at this. All of a sudden, they're jumping in phase. And this is a pretty extreme case, but just to kind of visualize what happens. So we're going along, and all of a sudden, they jump on us. Okay, let's see what happens. Well, all of a sudden, we're locked, and we jump out of lock immediately because the phase of the actual voltage sources have changed. They've jumped. It's a discrete step. So what happens is the controller starts actuating. Okay, we need to speed up here and get things moving. We want to drive the system back to steady state, and then it starts locking in and owning in here by about 0.22 milliseconds here. So that's a control effort trying to basically get this controller back into a lock state. You can see that immediately in the Q axis we're running along, we're good, and then we came out of lock, and then as the controller actuates we get back into lock. And again, this is a pretty extreme case. Having a phase jump of this much on the voltage lines is a pretty unrealistic case in reality, but just here we're doing this to illustrate how fast this controller can relock. We're talking only 10 milliseconds time here, less than a cycle of 60 hertz. So it's a pretty good response. Okay, let's check out another transient here. Now we're going to do something different here. We're going to check this response to a frequency step. So last one was phase, but this is going to be frequency. Okay, let's see what happens. So this happens at about 0.31 in time. So right here is where you're going to see the frequency jump. Now looking at this, the frequency jump was only 1 hertz. Now again, 1 hertz frequency jump, a discrete jump in frequency, is a pretty drastic case. But again here, just to illustrate how well this controller design will work here. So one thing, you'd like to see the jump, but it's pretty hard to see it because it's 1 hertz on top of 60. But essentially what's happening are these 3-phase waveforms are going at 61 hertz instead of 60 after time 0.31. Again, it's pretty hard to visualize because it's 1 hertz on top of 60, but these waveforms after 3.31 are going faster by about 1 hertz. Now you can see this almost immediately though in the Q axis. So what happens is all of a sudden we're at 0, that's where we want to be in steady state, right? We're locked down to 60, but the source jumps to 61 hertz, so our Q is going up, we're coming out of lock, we don't have our axis aligned, but our controller immediately starts actuating, which is nice. All right, and so what happens? The controller will push us into steady state. So let's call it somewhere about right here. We're back in lock, right? Q is back to 0. It means our Q axis is aligned with 0. We only have a D component. We're locked. But what's interesting is you look at U is non-zero, but U is now, this remember is essentially the delta omega. So if you take this and you add to it 60 hertz, well guess what? You get the 61 hertz that we are locking onto here. Okay, so that makes sense. And again, here's our phase output here, which is looking nice and clean. All right, so that was the control response to a step in frequency. Now let's take a kind of a more extreme case here. What we're going to do now is do something that may happen in reality. So we're going along, life is good, we're locked on, the voltages are balanced, we have 60 hertz, and at time 0.35 we have a 10% voltage imbalance. And actually I'll show you exactly where it is. So at about 0.35 in time we have a 10% imbalance on red, actually, this phase. Let's call it phase B here. And you can see it's actually less, so it's decreased by 10%. compared to the other phases. And what you notice now, essentially what we have is an unbalanced case, right? All three magnitudes of voltage source are not the same. And this actually reflects in the D steady state and the Q steady state. So what happens is now, because of this unbalance, you're going to get a second harmonic in your D and Q axis. So, okay, what does that mean now? We're not driving these two signals to DC because of this harmonic. Then what do we actually want to do? Well, what you'd like to do, at least for the Q axis, is you'd like to maintain the average at 0. I know there's going to be an AC component, again, because of the unbalance. But you want to drive the average to 0. Okay? And as long as you do that, you'll stay locked and you'll get the phase out properly, which is what's happening here. Okay? You have a little bit of a transient here at the beginning in order to get this controller back in there, but that's what you do. Now, you may say, okay, this is great, but it is varying a little bit. Can I do better? Yeah, there are more advanced applications where for this three-phase PLL that you can get a better response, and you can essentially get rid of the response of this harmonic. And what you're really going to want to do in that is basically extract your three-phase voltages into a positive sequence, negative sequence, and zero sequence, and then lock onto, for instance, the positive sequence. Okay? And what will happen is the imbalance will show up in zero sequence and potentially negative sequence. It depends on how bad your imbalance is and what type of imbalance it is. Okay, that concludes the discussion for the three-phase PLL. Thank you.
Okay, please submit any questions. I'm going to wait about 5 minutes, and then we'll go ahead and close the session for today. So please send me any questions, and we'll go ahead. And yeah, is this lecture available on the internet? It sure is. It's on CUSP. I believe it's cusp.umn.edu. So it should be here. Yeah, it looks like Jerry provided a direct link there, Gustavo. So Richard has a question about angles also affected by negative sequence. It is just hard to see. Absolutely. So I mean, the angle is definitely affected here in this because of course U is not DC after the transient, right? So if you take U and add it to omega natural or center and then integrate, that's what you get. You get this. But if very closely, there is just a little bit of angle variation. That is absolutely correct. And so, in a more advanced three-phase PLL, to account for an application where you have a grid imbalance, or you may see significant grid imbalance, a way to get rid of this is to generate positive, negative, and zero sequence DQ axes and lock your controller on and drive Q to zero in the positive sequence. And then your controller is no longer susceptible to imbalance like this. This isn't bad. It's not terrible, but it's not, we could do better, right? So there is you're integrating this. So essentially, I don't know, let's call this plus or minus 25, roughly, this sine wave here. You're adding that to a fixed 377 if you're at 60 hertz and integrating. So yeah, the angle is effective. That is for sure. So please send me questions. I'm going to wait in another couple, 3-4 minutes here, and let me know if you have more questions. Yeah, so I don't know about vector control. That's not mine. I'm not sure how that's scheduled, but I anticipate starting at 8:30 tomorrow, like usual. I have 2 more modules. Plus, if people are interested, we can go a little bit further into some of the ones that I'm still generating. Yeah, so it looks like they'll both be at the same time. I'm unsure because I don't run that course. Yeah, you're welcome, Eric. Not a problem. Thank you for all the questions. You guys are welcome. Gustavo and Gerarium, you're welcome. You're welcome, Morteza. Okay, I'm going to go ahead and conclude this meeting. Thank you, everybody, for participating. We'll see you tomorrow at 8:30. And again, if you have additional follow-on questions or comments, please make sure you email them to me. Thank you. We'll see you all tomorrow. Thanks for all your great questions, Richard. We'll see you tomorrow. You're welcome, Jose. We'll see you tomorrow.